Hello there, and welcome to Life Beyond Scene, a place where we take questions that usually stay in the background of daily life and let them unfold slowly, calmly, in a way that feels less like a lecture and more like a gentle conversation you can drift along with. Tonight we're setting our curiosity toward a question that might sound simple at first, but grows stranger the longer you think about it. Why have we managed to travel hundreds of kilometers above the Earth into orbit, walked on the Moon, sent probes across the solar system, yet we have not explored in equal detail the great depths of our own oceans? We look up and build rockets that withstand vacuum and cosmic radiation, but when we look down into the water that covers most of our planet, we realise how little we've actually gone. The question is both practical and philosophical. Why does one direction seem open to us while the other remains closed? Why do we speak with such confidence about galaxies millions of light years away, yet still admit that we know more about the surface of Mars than the floor of the sea that lies right here at home? As you settle in, perhaps in bed, perhaps with dim light and a quiet room around you, I'd like to ask you something. When you think of mystery, do you feel it more when you look up at the night sky, or when you imagine the black water beneath the waves? Maybe it depends on the day. For some, the stars call more loudly, or for others, the thought of what swims in the unseen depths feels closer, sharper. Either way, both directions ask us to imagine beyond the familiar, and both directions remind us of limits in what humans can do. Where are you listening from tonight? Maybe you're near the coast, where the ocean's presence is part of daily life. Or maybe you're far inland, where water seems smaller but the sky feels endless. Wherever you are, the wonder remains. Above you, a universe. Below you, a world we've barely entered. If you find these quiet wanderings a gentle way to unwind, it would mean a lot if you gave the video a like or subscribed so you can join future nights of curiosity. It's a small way of helping this calm corner of science and storytelling reach others who may need it. And don't worry, the goal isn't to keep you awake all night with questions. If the sound of this voice helps you drift off, then perhaps by the time you sleep you'll be carried along by thoughts of distant galaxies or hidden ocean trenches. Either way, the mysteries will still be here when you wake. When people talk about the ocean and space, they sometimes imagine them as opposites. But in truth, they share more than most of us realise. Both are vast, both are inhospitable, both surround us with scales too large for ordinary human senses. They both force us to rely on machines, calculations, and courage to move through them. And both, in their own ways, have shaped our imaginations. Myths of the sea with creatures rising from the depths, myths of the sky with gods and stars mapping destinies. In the modern world, we translate those myths into science, but the awe doesn't disappear. If anything, it grows. Think about how many people can name famous astronauts, the Apollo missions, the International Space Station, yet how few can name the people who descended into the Mariana Trench, or the machines that crawl the sea floor. This imbalance is part of what makes our central question so important. Why has one frontier captured so much attention while the other remains hidden? Part of the answer lies in how we think of distance. When we say space is far away, we picture the rocket climbing higher and higher, leaving Earth behind, travelling beyond the air. That feels enormous. But when we speak of the sea, the maximum depth is a mere 11 kilometres. On paper, that's tiny compared to the 384,000 kilometres to the Moon. It should be easier. Yet easier doesn't always mean safer or more accessible. Depth brings with it crushing pressure, darkness, cold, and unpredictability. A rocket may need to escape Earth's pull, but once it clears the atmosphere, the vacuum of space is in some ways simpler to engineer against than the constant, increasing pressure of water that grows by a full atmosphere every 10 meters. In space, a spacecraft holds pressure inside. In the sea, a submersible must withstand pressure pressing in from all directions. The difference is not just a matter of strength, but of design philosophy. And that difference begins to explain why space, as unwelcoming as it is, has been more open to exploration than the deep ocean right beneath our feet. But before we reach into those details, it's worth slowing down and noticing how these comparisons shape our perception of the world. When you imagine looking up, there's a sense of openness. The stars stretch outward with no visible barrier. When you imagine looking down into the ocean, there's a boundary right at the surface. You see water reflecting light. You know the world below continues, but vision stops quickly. That single moment of blocked sight makes the sea feel closed off. Our psychology leans toward what we can see. We explore where vision promises something more. And so, even before the physics and engineering enter the story, human minds already tilt the balance toward the sky. We imagine rockets leaving Earth more easily than we imagine the hidden landscapes of trenches, ridges, and hydrothermal vents that remain invisible. Our dreams, as much as our tools, steer us. This is also why the topic makes such a rich path to follow tonight. It isn't just about comparing technical obstacles, it's also about comparing the ways we think, the values we place on exploration, and how those values influence where governments, scientists, and private companies direct their energy. Going to space has long been tied to prestige, competition, and national pride. It has been a symbol of advancement. Meanwhile, sending people or machines to the bottom of the ocean hasn't carried the same cultural weight, even though it reveals landscapes more alien than Mars and creatures stranger than anything in science fiction. The balance is tilted not just by nature, but by culture. As we wander further into this story, we'll look at both histories, the upward climb into orbit and beyond, and the downward dives into the abyss. We'll see how technology evolved in both directions, why some paths were pursued more heavily than others, and what it tells us about the human urge to know. We'll talk about pressure, oxygen, temperature, and the limits of light. We'll compare rockets and submarines, astronauts and aquanauts, budgets and priorities. And we'll also pause to notice how mystery itself keeps calling us, no matter the direction. Some of those mysteries remain scientific, others remain psychological. Both will stay with us through this gentle journey. So, make yourself comfortable, breathe slowly. Let the idea settle in. We can leave the planet and touch the sky, but we can barely touch the full depth of the waters that cover most of it. Why is that? Why does one frontier feel within reach while the other remains hidden? These are the questions we'll drift through calmly, steadily, without rushing for an answer. Because sometimes the act of asking is enough to open the door to wonder. When we talk about what lies above us and what lies below, it's tempting to draw a sharp line between the two, as though space and the ocean were entirely separate realms with no connection at all. Yet when you pause and think about it, the similarities are more striking than the differences. Both are domains where human bodies are entirely unsuited to survive without help. Both stretch so far beyond our natural senses that we need instruments just to make sense of them. And both inspire stories of wonder, fear, and ambition, shaping the way we see ourselves in the universe. Imagine the view of a sailor hundreds of years ago, standing on a deck at night, staring upward at the stars while also aware of the black, endless sea beneath the ship. In both directions there was a mystery, one illuminated by points of light, the other hidden in silence and darkness. The sailor could map the constellations, navigate by their slow march across the sky, and still have no idea what swam just meters below. To this day, that duality hasn't left us. Satellites photograph entire continents in crisp detail, while huge portions of the ocean floor remain unmapped. Astronomers catalogue exoplanets orbiting distant suns, yet biologists continue to discover entirely new species in waters just a few hundred meters deep. That imbalance creates a strange tension. We seem to know more about the universe far beyond Earth than about the hidden world on our own planet. When people hear this, they sometimes assume it's because the ocean is simply less important, but the truth is more complicated. The sea is not only the source of life on Earth, but also a direct influence on weather, climate, and the balance of ecosystems. The upper atmosphere and outer space might be essential for satellites and global communication, but the ocean quietly supports every breath we take, producing much of the oxygen in our air. Yet despite this intimate connection, the sea still feels foreign. Perhaps the difference lies in the kind of mystery each presents. Space offers a mystery of distance. It invites us to dream of travel, of going somewhere else. The sea offers a mystery of concealment. It's right here, and yet it refuses to reveal itself without effort. One asks us to build vessels that soar. The other asks us to build vessels that endure. Both demand ingenuity, but the ways we respond to them reflect how humans weigh dreams against dangers. There's also the way light behaves. Look up at the night sky and you see stars from millions of years ago. They're like travelling through space until it finally reaches your eyes. Space gives us distance as time. We see the past every time we look up. But look down into the sea and light vanishes quickly. Within a few dozen meters, colours fade. Red disappears first, then orange, then yellow, until only blues and greens remain. Keep going, and even those fade into black. Instead of giving us the past, the ocean takes away the present. It blinds us, leaving us with only imagination. Both directions create mystery, but they do so in opposite ways. One overwhelms with information that comes from far away. The other hides information that is close at hand. Consider how language reflects this. We speak of the heavens with words like infinite, boundless, eternal. When we speak of the deep sea, we use words like abyss, trench, crushing, hidden. Both sets of words carry awe, but one leans toward hope and grandeur, the other toward fear and uncertainty. It isn't that one is truly safer than the other. Astronauts know how dangerous space can be. A single mistake can end a mission. Yet the language of space exploration is tied to progress and achievement, while the language of ocean exploration often feels tied to survival and endurance. That shift in perception influences not just public imagination, but also the funding, politics, and science that follow. Despite these differences, it's important to see how much both realms mirror each other. Astronauts and deep-sea divers share similar training, learning to operate in suits, managing limited oxygen supplies, living in confined spaces, facing isolation, and enduring psychological stress. Both must rely on technologies that separate them from direct contact with the environment. A spacesuit maintains pressure, warmth, and breathable air. A diving suit or submersible shell keeps water pressure at bay, and both must rely on communications with teams back on the surface of Earth. Neither astronaut nor diver is truly alone. They're both part of networks of engineers, scientists, and mission controllers who keep them alive. In that sense, space and sea exploration are less about individual bravery and more about collective effort. It's also striking how both the sea and the sky have served as metaphors for exploration throughout history. When writers in the Renaissance spoke of space, they often called it an ocean of stars. The first astronauts themselves described orbit as a kind of sailing, with the spacecraft as a fragile vessel moving through an endless sea. Likewise, when marine explorers descended into the depths, they spoke of it as venturing into an alien world. That sense of duality has never really faded. When you read the diaries of astronauts and submersible pilots side by side, you find the same mixture of fear and awe, the same awareness that they are intruders in a place not meant for them. And yet, one of those frontiers has been celebrated endlessly, while the other has remained obscure. School children around the world learn the names of Yuri Gagarin, Neil Armstrong, Buzz Aldrin. Far fewer learn the names of Jacques Piccard or Don Walsh, who reached the deepest part of the ocean back in 1960. Even fewer could name James Cameron, not for his films, but for his solo dive to the Challenger Deep in 2012. The imbalance isn't because the feats of ocean explorers are less impressive. It's simply that the stories of space have been told more widely. They've been tied to politics, technology, and global media in ways the sea never has. This brings us back to the shared mystery. Space and sea alike remind us of our limits. We breathe air at 1 atmosphere of pressure. Our eyes see light in a narrow band of wavelengths. Our skin tolerates only a limited range of temperature. Step too far in either direction, too high or too deep, and our bodies fail. That fragility is a constant reminder that humans are creatures of the surface. We belong in a thin band between sky and sea, yet we keep trying to leave it. There's something universal in that urge. Perhaps it's curiosity, perhaps it's restlessness, perhaps it's the need to measure ourselves against the unknown. Whatever it is, it drives us to build machines that compensate for what nature denied us. Both directions also raise questions about what it means to explore. Is it simply reaching a place and coming back alive? Or is it about learning, measuring, mapping, and sharing knowledge? In space, exploration often means putting satellites in orbit, telescopes on mountaintops, probes on other planets. In the sea, it often means sonar scans, remotely operated vehicles, and occasional manned descents. In both cases, exploration becomes less about the lone adventurer and more about the instruments that extend our senses. We may celebrate the astronaut planting a flag, but behind that image lies decades of engineering, vast networks of sensors, and teams working tirelessly to gather information. The same is true for the sea. A diver might describe the silence of the abyss, but most discoveries are made by machines quietly recording data in the dark. The mystery remains, but it is gradually transformed into knowledge by technology. When we put the two together, the sky above and the sea below, we see a mirror of human limits and ambitions. One reminds us how far we can reach. The other reminds us how close mystery can be even when it's right underfoot. Together they show that distance is not the only barrier. Sometimes concealment is just as effective. Sometimes the unknown doesn't need to be millions of kilometers away. It can lie a few hundred meters beneath the surface of the water, invisible, pressing inward, waiting. And as we move forward in this story, it's worth holding that thought. The mysteries above and below are not rivals, they're companions. Each tells us something about why humans explore, how we overcome challenges, and what we choose to value. Both are reminders that the surface where we live is a narrow margin between extremes, and that the drive to explore is not about comfort, but about curiosity. As we continue, we'll follow the histories of how humans began to rise upward into the air and beyond, and how we began to sink downward into the sea. Each story begins with simple tools, simple dreams, and each grows into complex machines and bold missions. And the more we see them side by side, the more we'll understand why one path became dominant while the other remained quiet. When we think about how humans began their journey into the sky and then beyond the atmosphere, it's easy to picture gleaming rockets and astronauts waving from capsules. But the story stretches back much further, beginning not with steel and engines but with imagination. For most of human history, the sky was a canvas of stories. The sun, moon, and stars were guides, clocks, calendars, and symbols. Before we ever considered escaping Earth's gravity, we used the heavens to organize our days, our harvests, and our myths. People charted constellations and built monuments aligned with solstices and equinoxes, evidence that the sky mattered deeply long before science formalized its study. Looking up was always the first step, even if travel was only in the mind. The first attempts to actually reach upward in a physical sense were modest. Fireworks in China more than 1,000 years ago used black powder to send small rockets into the air. They weren't built to carry people or equipment. They were built for spectacle and celebration, but they showed that thrust could be generated by controlled explosions. Over time, military uses followed. Gunpowder propelled arrows and small projectiles farther than muscle alone ever could. These early rockets were crude and unpredictable, but they set the foundation for the idea that perhaps one day, with refinement, something larger could be sent upward. Centuries later, in the early modern period, scientists like Isaac Newton began to work out the mathematics of motion and gravity. Newton's laws of motion describe not only how apples fall, but also how cannonballs arc through the air. And in one of his famous thought experiments, Newton imagined a cannon firing from a mountaintop with enough speed that instead of falling back to Earth, the cannonball would keep circling the planet. It was a purely theoretical picture at the time, but it hinted at the principle of orbit centuries before anyone had the tools to achieve it. The dream of leaving Earth had moved from myth to mathematics. By the 20th century, technology had caught up to those dreams. The development of liquid-fueled rockets in the early 1900s, pioneered by figures like Robert Goddard in the United States and Konstantin Tsiolkovsky in Russia, made space travel seem less like fantasy and more like a possible engineering challenge. Goddard built and launched rockets that rose higher and flew longer than any before. Tsiolkovsky wrote about multi-stage rockets, the idea of leaving Earth's atmosphere, and even concepts for space stations. These were still early steps, often met with skepticism, but they established the intellectual groundwork for what would become one of humanity's most ambitious endeavours. World War II accelerated rocket development, though in tragic and destructive ways. The German V-2 rocket, built under the direction of Wernher von Braun, was the first long-range guided ballistic missile. It struck targets hundreds of kilometres away and demonstrated the power of rocketry on a scale never seen before. After the war, both the United States and the Soviet Union sought to capture rocket technology and expertise. Von Braun and his team were taken to America, while Soviet engineers advanced their own designs. Out of military rivalry, the space age was born. In 1957, the Soviet Union launched Sputnik 1, a polished metal sphere about the size of a beach ball, into orbit around the Earth. It was simple by today's standards, transmitting little more than radio beeps, but it changed everything. For the first time, humanity had placed an object beyond the atmosphere circling above. The sky was no longer a boundary, it was a route. The world reacted with awe, excitement, and fear. If a satellite could orbit the Earth, then rockets could potentially deliver much more, whether scientific instruments or weapons. This dual reality defined the era. The United States responded quickly, launching Explorer 1 in 1958, which carried instruments that discovered the Van Allen radiation belts around Earth. That same year, NASA was founded, consolidating various research programs into a dedicated civilian agency for space exploration. From that moment forward, the race to space became a central story of the Cold War, one that would push technology forward at incredible speed. The next milestones came in quick succession. In 1961, Yuri Gagarin, a Soviet cosmonaut, became the first human to orbit the Earth. His flight aboard Vostok 1 lasted just 108 minutes, but it proved that people could survive launch, orbit, and re-entry. Gagarin became a global hero, his smile and calm demeanour broadcast worldwide as symbols of human achievement. The Americans followed soon after with Alan Shepard, the first American in space, and John Glenn, the first American to orbit the Earth. Each mission was short by today's standards, but each pushed the boundary of what seemed possible. As rockets grew more powerful and missions more ambitious, the Moon became the next target. President John F. Kennedy famously declared in 1961 that America would land a man on the Moon and return him safely to Earth before the decade was out. At the time, the idea seemed nearly impossible. The technology had not yet been developed, the knowledge incomplete, the risks enormous, and yet, driven by national rivalry and human determination, the Apollo program was born. Over the next several years, engineers designed the Saturn V rocket, still one of the most powerful machines ever built. Test flights and tragic failures, like the Apollo 1 fire that killed 3 astronauts, underscored the dangers, but progress continued, and in 1969 Apollo 11 carried Neil Armstrong, Buzz Aldrin and Michael Collins to the Moon. When Armstrong stepped onto the lunar surface, the world watched. His words became part of history, but beyond the symbolism, the achievement marked the first time humans had travelled beyond Earth's gravity well, landed on another celestial body and returned. The missions that followed collected rock samples, deployed scientific instruments, and gave humanity its first direct knowledge of another world. By 1972, 6 Apollo missions had landed astronauts on the moon. And then, just as suddenly, the program ended. Political will shifted, budgets tightened, and the grand adventure paused. But space exploration did not stop. Satellites became essential for communication, weather forecasting, and navigation. Probes like Voyager, Pioneer, and Viking extended human reach to the outer planets and even beyond the solar system. The International Space Station became a symbol of cooperation, with astronauts from many nations living and working in orbit for months at a time. The shuttle program launched reusable spacecraft, though it carried its own risks and tragedies. Private companies eventually joined in, lowering costs and rekindling excitement. What had once been a race between superpowers evolved into a more complex landscape of science, commerce, and international collaboration. All of this grew from that simple act of looking up and asking what lies beyond. Rockets and satellites, astronauts and probes, each step upward revealed not just new knowledge of the cosmos, but also new perspectives on Earth itself. Astronauts often speak of the overview effect, the profound shift in perception that comes from seeing the planet as a fragile sphere floating in the vastness of space. It reminds us of both our achievements and our vulnerabilities. Space exploration, while technically about leaving Earth, has always reflected back on Earth in surprising ways. And yet, while we celebrate the history of looking up, it's worth remembering how intertwined it is with politics, culture, and economics. Rockets were built because nations wanted power and prestige. Satellites launched because governments needed communication and intelligence. Astronauts became icons because they symbolized progress. Scientific curiosity was always present, but it often rode alongside strategic interests. This doesn't lessen the achievements, but it helps explain why so much effort went upward, while the ocean remained comparatively neglected. Looking up aligned with global competition. Looking down did not. Still, the history of rockets, satellites, and first steps beyond Earth is one of humanity's defining stories. It shows how quickly imagination can turn into reality when resources, ambition, and urgency align. In less than a century, humanity went from small fireworks to footprints on the moon. That acceleration is astonishing, and it continues today as new missions aim for Mars, new telescopes peer into the early universe, and new companies plan for tourism in orbit. The sky is no longer the limit, it's just the beginning. And as we trace that upward journey, it becomes even more striking to place it beside the downward journey into the sea. While rockets soared higher and higher, submersibles crept slowly downward, facing challenges of their own. The comparison between the two tells us not just about technology, but about human priorities. The sky called loudly, and we answered. The sea remained quiet, and so we often ignored it. Yet the mysteries there are no less profound. To understand why, we must now turn from the story of ascent to the story of descent, to the history of how humans first tried to look into the depths below. When we shift our attention downward instead of upward, the story begins in a much more humble and improvised way. For as long as humans have lived near water, the question of what lies beneath has been impossible to ignore. The surface may glitter under sunlight or whip itself into storms, but beneath it lies silence, darkness, and something hidden. People needed to fish, harvest sponges, collect pearls, and recover objects that had fallen into the water. Long before there was any dream of submarines, the simplest form of exploration was just the human body holding its breath. Free divers could descend a few meters, sometimes more, relying only on lung capacity and courage. For centuries, this was the main way the ocean gave up its secrets. Pearls from oysters, sponges for daily use, and even stories of treasure recovered from shipwrecks came from people who trained themselves to push the limits of their own physiology. In those early times, the ocean remained less a place of discovery and more a place of survival. Eventually, the desire to go deeper led to the first tools. In ancient Greece, more than 2,000 years ago, there are accounts of simple devices called diving bells. Imagine an inverted container heavy enough to sink lowered into the water with its open side down. Air would be trapped inside, creating a pocket that a diver could enter and use to breathe. The earliest versions were crude, but they extended the time a person could remain underwater. The diver could emerge into the bell, catch breath, and then continue working. The concept is straightforward by modern standards, but in its time it was revolutionary. Instead of being entirely limited by a single breath, humans had created a way to carry air into the depths. During the Renaissance, the diving bell was refined further. By the 16th and 17th centuries, engineers across Europe experimented with bells that could hold multiple people and be resupplied with air through hoses. Some of these contraptions were little more than wooden barrels or metal chambers, but they allowed divers to descend to depths of 20 or 30 metres, staying submerged for longer periods. Salvage operations became possible on a new scale. Sunken ships, lost cargo, and valuable materials could be retrieved, and as commerce grew, so did the importance of reaching what had fallen beneath the waves. Even so, these early efforts only scratched the surface. The ocean was vast, and most of it remained inaccessible. A few dozen metres down was impressive for its time, but it barely touched the world of trenches and ridges that stretched kilometres below. The pressure was too intense, the light too absent, the cold too overwhelming. For centuries, the deep sea remained a place of imagination. Myths of sea monsters, leviathans and krakens filled the gap left by a lack of direct experience. Sailors might have feared storms, but they feared the unknown of the deep even more. By the 18th and 19th centuries, technology began to improve again. The invention of air pumps and helmets connected by hoses allowed divers to remain underwater while receiving a constant supply of air from the surface. These hard-hat divers, wearing heavy metal helmets and weighted boots, became icons of the industrial age. They could walk along the sea floor, tethered to ships by long hoses and ropes. Their presence transformed underwater work. Ports could be built more efficiently, shipwrecks could be explored more systematically, and the sea began to look less like a forbidden world and more like a challenging workplace. Still, the tether was both lifeline and limit. Divers could not roam far, and any failure in the air hose was deadly. The dream of a fully independent underwater vessel began to grow. In the early 1600s, Cornelius Drebbel, a Dutch inventor working in England, is credited with building one of the first rudimentary submarines. His device, described in scattered accounts, was little more than a rowboat covered with greased leather, propelled by oars that poked through tight seals. It could submerge for short periods in the Thames River and reportedly carried a dozen men. While primitive, it proved the concept that humans could move beneath the surface in a sealed craft. Over the next centuries, inventors across Europe and America experimented with similar ideas, producing various prototypes, many of which sank rather than swam. The 19th century brought more serious designs. Submarines began to use compressed air for buoyancy control, propellers for propulsion, and eventually engines. Many were built for military purposes, designed to sneak up on enemy ships. During the American Civil War, the Confederate vessel Hunley became the first submarine to sink an enemy ship in combat, though it also sank itself in the process. Submarines of this era were dangerous and unreliable, but they showed a growing determination to master the environment below the surface. At the same time, scientific curiosity about the ocean was growing. Expeditions like the famous voyage of HMS Challenger in the 1870s began mapping depths and cataloguing species. Nets were dropped into the abyss and pulled back with creatures never seen before, some so strange they looked like products of imagination. For the first time, the ocean floor was studied systematically, though it remained out of reach for direct observation. In the early 20th century, a few visionaries began to think about how to actually send people into the abyss safely. One of the most famous attempts came from William Beebe and Otis Barton in the 1930s. They built a steel sphere called the bathysphere, connected to a ship by a steel cable. Beebe and Barton would climb inside, the hatch would be sealed, and the sphere would be lowered slowly into the depths off Bermuda. Through thick quartz windows they could peer out into the darkness. On their deepest dive, they reached more than 900 meters, setting a record at the time. Beebe described strange glowing creatures, bioluminescent fish, and shapes that looked almost alien. Though the bathysphere had no mobility of its own, it was entirely dependent on the cable. It opened a window to a world that no one had seen before. This marked the beginning of direct human descent into the deep. Later designs improved on the bathysphere. Auguste Piccard, a Swiss physicist and inventor, designed the bathyscaphe in the 1940s. Unlike the bathysphere, which relied on being lowered from a ship, the bathyscaphe was a free-diving vessel. It used a gasoline-filled float for buoyancy and iron ballast that could be released to allow it to ascend. With his son Jacques, Piccard launched the bathyscaphe Trieste. In 1960, Trieste carried Jacques Piccard and Don Walsh of the US Navy to the Challenger Deep, the deepest known point in the world's oceans, nearly 11,000 meters down. They spent about 20 minutes at the bottom before releasing ballast and rising back to the surface. The descent took nearly 5 hours. The pressure outside their sphere was more than 1,000 times greater than at the surface. They reported seeing flatfish-like creatures and sediment stirred by their landing. The achievement was extraordinary, yet it did not lead to widespread exploration. For decades after, no one returned to those depths. While submarines became advanced military machines, capable of travelling silently for weeks underwater, scientific submersibles remained rare and expensive. In the 1970s and 80s, vehicles like Alvin allowed scientists to study mid-ocean ridges, hydrothermal vents, and unique ecosystems teeming with life around hot mineral springs. These discoveries revealed that life could thrive without sunlight, relying on chemical energy instead of photosynthesis. The implications were enormous, hinting that life on other worlds might not require sunlight either. Still, such missions were limited in number. For every launch into space that captured public imagination, there were only a handful of deep-sea dives that quietly advanced knowledge. By the time James Cameron descended solo into the Challenger Deep in 2012 with the Deep-Sea Challenger, he was only the third human to ever visit that place, more than 50 years after Piccard and Walsh. The technology had improved, with cameras and instruments gathering data, but the fact remained. In half a century of technological growth, we had gone to the moon, built space stations and sent probes across the solar system, yet we had almost entirely neglected the ocean's deepest point. The story of looking downward is a story of bursts of progress followed by long pauses. Diving bells gave way to hard hat divers, submarine prototypes gave way to steel spheres. The Trieste proved that the deepest trenches could be reached, but few followed. Even today, most of the ocean floor has been mapped only by sonar, not by direct observation. Vast regions remain unseen, unexplored, and unnamed. The reasons are partly technical, partly financial, and partly cultural. But the mystery is still there, waiting. The history of descending into the sea is not just about machines and records. It's about the persistence of curiosity in the face of limits. Every attempt to go deeper faced obstacles that seemed insurmountable, pressure that could crush steel, darkness that no lamp could fully pierce, and the sheer difficulty of building machines that could survive and return safely. Yet people kept trying. From ancient divers holding their breath to modern engineers designing titanium spheres, the urge to see beneath the waves has never gone away. And as we hold this story beside the history of rockets and satellites, the contrast sharpens. One direction became a global obsession. The other remained the pursuit of a few individuals and small teams. Both revealed wonders, both expanded our understanding, and both reminded us how small we are compared to the environments that surround us. One showed us new worlds above, The other showed us alien landscapes below. Both continue to shape the way we imagine our place in the universe. As we continue, we'll look more closely at why the two directions pose such different challenges. We'll see how gravity, pressure, and the limits of air shape the possibilities. We'll compare the expansion of rockets to the crushing force of the ocean, and in doing so, we'll move one step closer to answering why humans have travelled so confidently into space, while only tiptoeing into the deep sea. When people think about leaving Earth, they usually imagine the enormous roar of a rocket engine, flames pouring out, a craft straining against gravity until it finally breaks free and climbs into orbit. The effort seems monumental, and it is. Every kilogram of payload must be accelerated to thousands of kilometers per hour to balance against Earth's pull. The numbers are daunting. To stay in orbit around Earth, an object must travel about 28,000 kilometers per hour. To escape Earth entirely, the speed climbs higher still, around 40,000 kilometers per hour. That kind of acceleration requires engineering at the very edge of human ability, vast quantities of fuel, and careful calculations. Reaching orbit is not just a matter of climbing, it's a matter of speed. If a rocket rose straight up and stopped, it would fall back down again. It must curve sideways fast enough that as it falls, the Earth curves away beneath it. Orbit is essentially falling forever, but missing the ground. The sheer scale of this task makes the story of spaceflight impressive, but it can create a misleading comparison. People often imagine that diving into the sea must be simpler, because the depths are only a few kilometers away, while space begins just over 100 kilometers above. The reality is more complex. Sinking into the ocean doesn't require fighting gravity in the same way, but it requires resisting the pressure of the environment. Every 10 meters deeper adds the equivalent of another atmosphere pressing on every surface. At 1,000 meters down, that's about 100 times the pressure at sea level. At the bottom of the Challenger Deep, it's over 1,000 times. Unlike space, which is nearly empty and exerts no pressure at all, the ocean bears down relentlessly on anything that dares to enter. In space, the problem is acceleration. In the ocean, the problem is compression. A spacecraft must generate enormous thrust to overcome gravity's pull, but once in orbit it's mostly coasting. A submersible, by contrast, can descend with little effort. In fact, gravity helps. It sinks on its own. The challenge is not getting down, but surviving the squeeze as the water tries to crush the hull. Instead of engines, the engineering problem is strength. How do you build a vessel that won't collapse under pressure? How do you design windows thick enough to resist tons of force yet still allow a human eye to see through? These two environments demand opposite strategies. Spacecraft are lightweight, designed to minimize mass so that rockets can lift them. Submersibles are heavy, often built with thick metal spheres because weight is less important than resisting pressure. One fights gravity with speed, the other fights pressure with brute strength. Both require careful balances of materials, design, and safety margins. Both punish mistakes without mercy. There's another difference worth noticing. Rockets need enormous amounts of energy up front, but once in orbit, the environment is stable. A spacecraft can circle Earth for years with little more than occasional corrections. Submersibles, on the other hand, face constant resistance. Water is dense, much denser than air. Moving through it requires energy at every moment. A submersible cannot glide effortlessly the way a satellite can. It must push against the drag of water, fighting its way through a medium that resists motion. Even communication is affected. In orbit, radio waves travel freely through the vacuum. In the sea, signals are quickly absorbed or scattered, limiting contact with the surface. The environment itself shapes the possibilities. Humans themselves illustrate the difference even more starkly. An astronaut in orbit floats weightless, shielded inside a pressurized cabin, but essentially free from the crushing force of gravity. They experience microgravity, where objects drift, and even a feather moves the same as a hammer. A diver descending into the sea feels the opposite. Every breath, every movement is against increasing pressure. Their lungs compress, their blood chemistry shifts, their body reacts in ways it was never designed to handle. One environment liberates the body from weight, the other weighs it down relentlessly. It's fascinating that the word escape is used for spaceflight. The idea is that you must escape Earth's pull, break free and enter a realm beyond. In the ocean, the journey is not escape but endurance. You're not leaving Earth. You're burying yourself within it, surrounded on all sides by its most ancient element. The difference in language reflects the difference in challenge. One is about speed and release, the other is about strength and survival. Still, when you place the two side by side, the contrast begins to explain why spaceflight has advanced more visibly than deep-sea exploration. Rockets are dangerous, expensive, and complicated, but once the energy problem was solved, progress accelerated. Submersibles, by contrast, continue to face the unyielding problem of pressure. You can't burn more fuel to make the water less dense. You can't speed up to reduce pressure. The problem is not one of energy, but of physics itself. There's no way around the crushing weight except to resist it directly, and that makes the task harder to scale. Even today, when rockets can carry satellites, telescopes, and even tourists into orbit, only a handful of vessels have ever reached the deepest parts of the ocean. The difference isn't just money or interest, it's that the barriers scale differently. Spaceflight has a high entry cost but then expands outward. Deep-sea exploration has a constant cost, one that grows relentlessly with every metre downward. In some ways, you could say the sea is more hostile than space. In orbit, you must bring your own air and shield against radiation, but the vacuum itself doesn't try to crush you. In the ocean, the environment is actively trying to collapse whatever you bring. And yet, despite these differences, both realms reveal something profound about human ingenuity. Rockets and submersibles both reflect the same principle. Building a small bubble of Earth-like conditions and carrying it into an environment where humans cannot survive alone. A spacecraft is essentially a portable slice of atmosphere, pressure and temperature. A submersible is the same, a little pocket of air and normalcy carried into a world of darkness and pressure. Both are fragile, tiny against the scale of what surrounds them. Both depend on layers of engineering and planning, and both remind us that survival in extreme environments is never natural. It's constructed, fragile, and temporary. The psychological difference also matters. Spaceflight is framed as triumph over gravity, a declaration that humans can rise above their planet. Submerging into the ocean is framed as intrusion, venturing where we do not belong. The one is celebrated as a victory. The other is often seen as a dare. That perception shapes funding, media attention, and the stories we tell. A rocket launch is broadcast live with millions watching. A record-breaking dive into the deep sea might be reported briefly then forgotten. Yet technically, both are equally remarkable. One overcomes gravity, the other overcomes pressure. Both push the boundaries of what machines and humans can endure. If we step back and compare them not as opposites but as complements, we see how they complete each other. The sky challenges us to move outward. The sea challenges us to move inward. One expands the horizon, the other deepens it. One is infinite in scale, the other infinite in density. To reach orbit, you must generate unimaginable force for a short time. To reach the deep, you must withstand unimaginable force for as long as you remain there. Neither is forgiving. Both are humbling. The balance between escaping upward and sinking downward explains why our worldviews have been shaped more by rockets than by submersibles. The spectacle of launch, the image of Earth from space, the symbolism of a flag planted on the moon, these are dramatic moments that capture the imagination. The descent into the abyss, by contrast, is slow, silent, and invisible to the public eye. Yet both are part of the same human impulse, to go where we are not supposed to see what lies beyond the boundaries of comfort. As we move further in this journey, it becomes clear that the differences between space and sea are not simply technical. They reflect two faces of the same challenge: how to carry fragile human life into environments that do not welcome it. Gravity asks us to leap. Pressure asks us to resist. Together they frame the story of why we have gone so far into space and yet so little into the ocean. And as we continue, we'll see how the need to breathe, the presence or absence of air, adds another layer of difference, shaping what is possible in both directions. When most people picture the dangers of space, they think of the vacuum, the absence of air, the emptiness that would freeze or suffocate a human body. But emptiness does something curious. It pulls outward. If a spacecraft cracks, the air inside rushes out violently, expanding into nothing. In the sea, the danger is the exact opposite. The ocean doesn't take away pressure. It adds more with every meter you descend. If a submersible cracks, water doesn't gently seep in. It slams inward with crushing force. The two environments, space and sea, seem like opposites, but both are extreme, both unforgiving, and both shape the way humans attempt to explore them. At the surface of the Earth, where we live, pressure feels invisible. One atmosphere pushes down on every square centimetre of our skin, but our bodies are balanced to it. We don't feel crushed because the fluids inside us push back with equal force. Life evolved under this condition, so it feels natural. It's only when we leave this balance that the reality of pressure shows itself. Climb a tall mountain and the air grows thin. Descend into the sea and the pressure grows heavy. Both directions remind us that our comfort zone is astonishingly narrow. The sea enforces its limits faster. Just 10 metres below the surface, pressure doubles. At 100 metres, it's 10 times what we feel on land. By 1,000 metres, the numbers are staggering. At the deepest trenches, the pressure is equivalent to several hundred jumbo jets balanced on a single human body. For a machine, even a small crack or weak spot can mean immediate collapse. That's why deep-sea vessels are often built as spheres. A sphere distributes pressure evenly across its surface. Flat panels, which are common in spacecraft design, would buckle instantly under such loads. Spacecraft are designed to contain air. Submersibles are designed to resist water. The priorities diverge entirely. It's interesting to think of how different the forces act. In space, the problem is internal. The air pressure inside the craft is higher than the pressure outside, so the hull is always being pushed outward. Engineers must design it so that it doesn't rupture from within. In the ocean, the problem is external. The pressure outside is always greater, squeezing inward. Instead of containing, you are resisting. One environment tries to pull your air out, the other tries to crush you flat. Both are absolute in their danger. In space, a hole the size of a coin can vent air so fast that survival becomes impossible in seconds. In the ocean, a hull failure can implode so quickly that the vessel is destroyed before the crew has time to register what happened. The forces are different in direction, but similar in their refusal to forgive error. The difference in pressure also shapes how long humans can remain in these places. Astronauts in orbit, once safely enclosed, can stay for months, even a year, because the environment inside their capsule remains constant. Deep-sea divers, however, are limited not just by oxygen supply, but by the way their bodies respond to pressure. Breathing gases at depth changes the chemistry of the blood, creating risks like nitrogen narcosis, oxygen toxicity, or decompression sickness. Even if the equipment works perfectly, the human body itself becomes the limit. That's why submersibles are preferred for the greatest depths. Unlike space, where the body can be protected by maintaining pressure, the ocean demands shielding from pressure itself, and our biology cannot adapt beyond a certain point. There's also the question of scale. The vacuum of space is the same everywhere. Once you've built a spacecraft that can withstand it, you can travel to any altitude beyond the atmosphere without needing to strengthen the hull further. Pressure in the ocean, however, increases with every metre. A submersible designed for 1,000 metres cannot survive at 5,000 metres. Each design is specialised, each new depth a new engineering problem. That's why so few vessels have ever reached the bottom of the deepest trenches. Each attempt requires materials and designs at the very edge of what technology allows. Material science tells much of the story. Aluminum and steel, common in spacecraft, struggle under extreme compression. For deep-sea vehicles, engineers turn to titanium, hardened steels, and even ceramics. Glass, when shaped into thick spheres, can withstand incredible pressure and is sometimes used for instrument housings. But no matter the material, the ocean's pressure imposes absolute limits. If you want to go deeper, you must build stronger, thicker, heavier. There's no shortcut. The ocean punishes optimism with collapse. One of the most dramatic ways to grasp the difference is to imagine what would happen if a human body were exposed directly to each environment. In space, without a suit, the air in the lungs would rush out. Water vapour would boil from saliva and the moisture on the tongue. Consciousness would fade in seconds due to lack of oxygen. It sounds horrific, but the body wouldn't explode. Instead, it would suffocate and freeze. In the ocean's depths, by contrast, a human body would be crushed instantly. Bones, organs, tissues, all compressed in an instant under thousands of tons of force. Both scenarios are fatal, but the imagery they conjure reveals why the sea feels in some ways more terrifying. Space is absence, the sea is weight. One takes away, the other overwhelms. Pressure doesn't just affect machines and bodies, it also shapes ecosystems. Deep-sea creatures survive under immense pressure, and their biology reflects it. Proteins in their cells are structured to remain stable under compression. Membranes are adapted to resist collapse. Many cannot survive if brought to the surface. The pressure difference destroys them. In space, by contrast, no natural organisms exist outside Earth. Life there is impossible without a protective shell. The sea, despite its crushing force, is still full of life. This makes it both more accessible and more complex. Exploring space means protecting humans from vacuum. Exploring the sea means entering an environment already alive but alien to our biology. Even simple numbers highlight the difference. At sea level, pressure is about 14 pounds per square inch. At the bottom of the Mariana Trench, it's more than 16,000 pounds per square inch. Imagine every square inch of a vehicle's surface bearing the weight of a car. That's what deep-sea explorers face. Spacecraft, by comparison, deal with the single atmosphere of pressure inside. The challenge isn't resisting more and more as you go, it's keeping the air inside from escaping. Both require care, but the scaling of the problem is radically different. This difference also explains cost. Spacecraft can be mass-produced once a design proves itself. Satellites, for example, are now launched by the thousands. Deep-sea submersibles, on the other hand, are often one-of-a-kind machines, each custom-built for a specific depth. Few are ever constructed, and fewer still are capable of venturing into the greatest trenches. That scarcity means less experience, less infrastructure, and slower progress. The pressure problem also affects the psychology of exploration. In space, astronauts look out windows and see stars, Earth, and vast horizons. In the deep ocean, submersible windows reveal only darkness. Light from lamps fades quickly. The sense is not of expansion, but of enclosure. The mind reacts differently to being surrounded by emptiness than to being surrounded by crushing weight. This difference may be subtle, but it shapes the way both explorers and the public perceive these journeys. The paradox of space and sea is that one expands while the other compresses. Space makes things spread. Gases expand, bodies swell, fluids boil outward. The sea makes things shrink. Hulls buckle, bodies compress. Materials are squeezed tighter and tighter. Both reveal the same truth. Humans are fragile creatures living in a narrow range of conditions. The Earth's surface gives us just enough atmosphere and just little enough pressure for survival. Stray too far upward or too far downward, and nature reminds us immediately of our limits, yet both also remind us of resilience. With the right design, a spacecraft can circle Earth for years. With the right design, a submersible can descend into the deepest trenches and return. The physics is unforgiving, but the ingenuity is remarkable. Each challenge pushes materials, science, engineering, and human courage forward. Each reveals that even the harshest environments can be touched, if only briefly, by human presence. When you consider why we've gone so far into space but so little into the deep, the pressure problem is central. Escaping gravity was a hurdle, but once solved, the pathway outward opened widely. Resisting pressure is a never-ending battle. The deeper you go, the harder it gets, with no ceiling in sight until the very bottom. This doesn't make one achievement greater than the other. It makes them different. The sea resists every meter. Space resists only the first 100 kilometers. After that, emptiness rules. But at least emptiness doesn't grow heavier the farther you go. As we move on, the role of air and breathing becomes the next essential difference. Rockets must carry oxygen for engines and astronauts alike. Submarines must manage gases under crushing pressure, balancing chemistry as well as structure. In both cases, survival hinges on how we manage a resource we take for granted every moment of our lives. The contrast between airless space and oxygen-starved seas will take us deeper into why one realm has been explored far more than the other. When you pause to think about what it means to stay alive in an environment that doesn't welcome you, the first thing that comes to mind is air. Breathing is so constant, so automatic, that it rarely enters our awareness until it's interrupted. We don't wake up each morning grateful that oxygen's available at just the right concentration, held in balance by plants, oceans, and atmosphere. We only notice when it's gone, or when we imagine places where it isn't. That's where space and the deep sea both place their first obstacle. In one case there is no air at all, in the other there is plenty of oxygen, but it's bound up in water or exists in ways our lungs cannot use. In both directions our bodies are completely helpless without technology. Space presents the clearer contrast. Beyond Earth's atmosphere, there is simply nothing to breathe. Astronauts are entirely dependent on the air they carry with them, sealed inside their spacecraft or spacesuits. Every molecule of oxygen has to be brought from Earth or generated artificially, monitored constantly to keep the balance right. Too little, and suffocation begins. Too much, and the risk of fire becomes extreme. The famous Apollo 1 disaster was a reminder of this, when a cabin filled with pure oxygen ignited during a test and claimed the lives of 3 astronauts. In space, air itself is both necessity and hazard. Managing it safely requires systems of tanks, scrubbers, and careful design. The ocean, by contrast, is full of oxygen, but not in a form we can use. Fish extract dissolved oxygen through gills, but human lungs can't pull oxygen from water. When a diver descends, tanks of compressed air provide the supply, but the deeper they go, the trickier it becomes. Under pressure, the gases behave differently. Nitrogen dissolves more readily into the bloodstream, leading to nitrogen narcosis, a condition that clouds judgment and creates a kind of intoxication. Oxygen, too, becomes toxic at higher pressures, damaging tissues if breathed in high concentrations for too long. Divers must switch to special gas mixtures, helium-oxygen blends, trimix or rebreathers, that reduce these effects, but even then the limits remain. A mistake in managing gases can mean unconsciousness or death long before running out of oxygen itself. Submersibles face a similar challenge to spacecraft, creating a sealed environment where air is regulated, recycled, and kept at the right pressure. Carbon dioxide must be scrubbed from the atmosphere inside. Oxygen must be replenished. Unlike a spacecraft, which can vent waste gases into the vacuum, a submersible is surrounded by water at immense pressure, and venting anything is not simple. Systems must be built to keep air breathable for the entire duration of the dive. Engineers borrow techniques from both aviation and space programs, but the unique pressures of the ocean add complexity. There's also the question of emergencies. In orbit, if a spacecraft's air supply fails, astronauts can attempt to return to Earth quickly. though quickly in space still means hours. In the ocean, if a submersible's air fails, surfacing rapidly is not an option. Rising too fast creates decompression sickness, as gases dissolved in the blood form dangerous bubbles. The only safe path is slow and controlled, which is not always possible in an emergency. This makes oxygen management in the ocean even more critical. Where space punishes a lack of air with suffocation, the sea punishes both shortage and mismanagement with suffocation and decompression alike. For both environments, breathing becomes an exercise in trust. Astronauts trust their suits, their spacecraft, their life support systems. Divers trust their regulators, their gauges, their training. Submersible crews trust the closed environment designed by engineers. In each case, a single leak, a single system failure could mean disaster. On the surface of Earth, air feels infinite. In space or sea, air is finite, fragile, always measured. It changes the psychology of the explorers as much as it changes the technology around them. Many astronauts describe becoming intensely aware of their own breath, the sound amplified inside a helmet, each inhalation and exhalation a reminder of how dependent they are on the thin layer of technology separating them from death. Divers say the same of the hiss of a regulator. The rhythm of breathing becomes louder than thought. The need to manage air has shaped entire exploration strategies. In space, missions are planned around how much oxygen and carbon dioxide scrubbing material can be carried. Recycling systems on the International Space Station reclaim moisture and filter exhaled air, but the balance must always be maintained. In the deep sea, missions are limited by how much air can be stored in tanks or recycled through chemical scrubbers. Even when submersibles can withstand pressure for long periods, oxygen supply imposes strict time limits. Both frontiers are vast, but both force exploration into narrow windows, bound by how long a human can safely keep breathing inside an artificial bubble. The irony is striking. Earth's surface is wrapped in an ocean of air tens of kilometers thick, more than enough to supply every living thing. The oceans themselves contain dissolved oxygen, supporting life forms that have adapted to extract it. Yet the moment we leave our thin surface layer, either upward or downward, we lose access to this invisible gift. It reminds us that air is not universal. It is a product of Earth's particular history, photosynthesis, geology, and balance that makes this planet habitable. Space offers none of it. The deep sea hides it in forms we cannot use. Our lungs, so perfect for our narrow band of existence, are useless everywhere else. Even the training of astronauts and divers reflects this. Astronauts spend hours in neutral buoyancy tanks, practicing spacewalks underwater, not only because water simulates weightlessness, but also because it simulates dependence on breathing systems. Divers train to control panic, to stay calm when air feels limited because panic accelerates consumption. The slower and steadier the breath, the longer survival lasts. Breathing, so automatic on the surface, becomes a discipline in extreme environments. Calmness itself becomes a survival skill. When you compare the barriers side by side, the difference becomes clear. Space requires you to bring air from Earth and guard it carefully. The sea requires you to bring air and guard it, while also managing how pressure changes its chemistry. One is absence, the other is distortion. Both create absolute dependence on technology, but the sea layer's complexity on top of scarcity. This, too, explains why space has received more attention. The challenge of carrying oxygen into orbit is formidable, but once solved, it remains the same. The challenge of breathing at depth changes with every meter, requiring new mixtures, new limits, new systems. There is no universal solution. Each descent must be planned with its own breathing strategy. That makes scaling up exploration difficult. Rockets can be standardized. Submersibles must be customized. The breath itself becomes symbolic. In orbit, astronauts look down at Earth and see the blue atmosphere, thin and fragile, the very air they carry with them. they become acutely aware of its rarity. In the deep sea, explorers look out into the dark and feel the weight of water pressing against their hull, air compressed into a fragile bubble inside. In both places, the awareness of breathing becomes awareness of dependence, and dependence becomes awareness of fragility. In the end, the breathing barrier is not just technical, it's existential. It reminds us that humans are surface creatures, tied to a planet that provides exactly what we need in a narrow range of conditions. Outside that range, every breath must be earned by technology and planning. Exploration in either direction begins with solving the problem of air. It may sound simple, but it defines the boundary between life and death. As we move further into the comparison, another parallel emerges: temperature. Just as air becomes hostile beyond our surface, so does heat. Space is a realm of extremes, where direct sunlight can bake a spacecraft while shadow freezes it. The ocean is colder with every descent, reaching near freezing even in tropical regions. In both directions, humans must manage thermal barriers as carefully as they manage breathing, and in both, survival depends not only on what we carry with us, but on how well we understand the invisible forces waiting in silence, ready to remind us of our limits. When we think about environments beyond the surface of the Earth, one of the first questions that comes up is temperature. Our daily lives are shaped by modest variations in warmth and cold. A hot summer afternoon might feel overwhelming, a winter night might feel bitter, but the range of conditions we naturally tolerate is incredibly narrow. Our bodies thrive when the air around us is somewhere between a little above freezing and a little below 40 degrees Celsius. Even within that band, we rely on clothing, shelter and fire to stay comfortable. Beyond that band, survival becomes difficult. Space and the deep sea both exist far outside of it, but in opposite ways and with different consequences. In orbit, or even on the moon, temperature is dictated by sunlight. With no atmosphere to spread heat around, the side of an object facing the sun can become scorching hot, while the side in shadow plunges into freezing cold. On the moon, this swing is extreme. In daylight, the surface can climb above 120 degrees Celsius, hot enough to boil water. At night, or in shadow, it can fall below minus 170 degrees Celsius, cold enough to freeze almost everything solid. Space doesn't have weather. It doesn't have breezes to mix warmth and cold. It is a realm of direct extremes, with no buffer. A spacecraft must be designed with this in mind. Insulation, reflective surfaces, radiators and heaters are as important as engines and air supplies. Astronaut suits are built not only to hold air but also to manage temperature, with layers of insulation and systems that circulate water to carry heat away from the body. Without these measures, an astronaut in direct sunlight would overheat within minutes, while one in shadow would freeze. It is not the vacuum itself that holds a temperature. It is the absence of atmosphere that prevents balance. Space is less a place of steady cold and more a place where heat has nowhere to go. The deep sea, by contrast, is steady, but it is steadily cold. Sunlight warms the surface, but as you descend, the heat disappears. 100 meters down, light begins to fade, and with it warmth. By 1,000 meters, the water is close to freezing, hovering just above 0 degrees Celsius. In the deepest trenches, it remains that way constantly. Unlike space, where temperature swings between extremes, the deep ocean is locked in eternal chill. There is no day or night cycle, no warm breezes, no seasonal change. It is cold, always, everywhere. This difference shapes how we approach exploration. Spacecraft must prepare for both hot and cold, designing systems that can switch between them as a craft moves in and out of sunlight. Submersibles, on the other hand, must endure continuous cold. Heaters keep instruments and electronics from failing, but human occupants rely on the insulation of their vessel. If something fails in a submersible, the cold will seep in slowly but relentlessly. Unlike space, where sudden exposure can kill quickly, the sea enforces its chill gradually, sapping warmth over time. The danger is no less real. but it acts in a different way. It's interesting to notice how both environments exaggerate the conditions we already know. On land, we guard against heat stroke and frostbite, the dangers of too much or too little heat. In space, these dangers are amplified. In the sea, the danger of cold is amplified. Both remind us that our comfort zone is not universal. It is the product of Earth's surface conditions, balanced by atmosphere, weather, and currents. Remove those, and the balance collapses. The role of water in carrying heat is also critical. In space, with no air or water around, heat moves only by radiation. That makes it possible for spacecraft to control their temperature with reflective surfaces and radiators. In the ocean, heat moves easily. Water absorbs and transfers it far more efficiently than air. That means any source of warmth inside a submersible or diving suit is quickly drained. The ocean doesn't just stay cold, it actively pulls warmth away. This is why divers must wear thick wetsuits or dry suits even in tropical waters. Once submerged, the body loses heat 25 times faster in water than in air. For deep-sea creatures, the cold is not an obstacle but a constant. Their metabolisms are slow, their bodies adapted to conserve energy. Many produce their own light through bioluminescence rather than relying on warmth. Some use chemical reactions at hydrothermal vents, where heat from Earth's interior leaks upward to power their ecosystems. These vents create islands of warmth in the cold abyss, places where life flourishes despite the surrounding chill. The contrast is remarkable. In space, there are no natural oases of warmth except stars themselves. In the sea, heat wells up from cracks in the crust, creating pockets where organisms gather. The difference shows again how each environment shapes not only machines but life itself. Humans, though, remain tied to their narrow range. Astronauts rely on carefully balanced systems to keep them in comfort as they float between sunlight and shadow. Submersible crews rely on heaters and insulation as they descend into water that never rises above freezing. Both environments turn the act of staying warm into an engineering problem. On Earth's surface, warmth is free most of the time. Away from it, warmth is work. There's also a psychological side to this. Astronauts stepping into sunlight during a spacewalk know that just inches away, their suit is protecting them from searing heat. A turn into shadow, and it's protecting them from deadly cold. That awareness sharpens the sense of fragility. Deep-sea explorers, meanwhile, know that outside their hull is endless black water, at near freezing temperatures. A chill so complete that survival without protection would be measured in minutes. Both experiences remind them that comfort is not natural in these places. It is artificial, maintained by machines that must never fail. The contrast between space and sea temperatures also influences how we think about each frontier. Space is often imagined as a realm of fire and ice, extremes that swing wildly. The sea is imagined as uniformly cold, a place of silence and stillness. Both images are accurate in their own ways, and both shape the stories we tell. One is dramatic, with heat and cold in conflict. The other is steady, with cold pressing in endlessly. Both are alien to our everyday lives, but in different ways. When you consider why humanity has focused more on space than on the deep, temperature plays a subtle role. The design challenges of space are extreme but predictable. Engineers can calculate exactly how much heat a spacecraft will absorb in sunlight and how much it will lose in shadow. Solutions can be built into every mission. The sea, while seemingly simpler, adds complexity because cold interacts with pressure, breathing gases, and energy consumption. It makes every mission into a problem of endurance, not just insulation. And yet, the two extremes also share something important. Both force humans to carry their own bubble of warmth wherever they go, whether in a spacecraft orbiting Earth or a submersible descending into the abyss. The vessel becomes a miniature Earth, holding not just air but temperature within its walls. A reminder that what we take for granted on the surface, warmth, air, pressure is fragile, temporary and rare in the broader universe. This duality of heat and cold sets the stage for another commonality between space and sea: darkness. As light fades in both directions, new challenges arise. In space, the blackness of the cosmos surrounds everything beyond the sunlit surfaces. In the sea, sunlight disappears within a few hundred meters, leaving an endless midnight zone below. Darkness, like pressure and temperature, becomes a boundary. And to push against it, humans need lamps, sensors and imagination, just as much as they need courage. Darkness is one of the most immediate qualities of both space and the deep sea, yet it takes very different forms depending on where you look. When we step outside on a clear night far from city lights, we see darkness filled with stars. It's not the absence of light, but rather a canvas dotted with points that travelled across unimaginable distances to reach our eyes. Even when we call the sky dark, it never feels empty. It is crowded with galaxies, planets, and satellites drifting silently above. The deep sea is the reverse. As soon as you leave the shallow surface waters, light disappears in a matter of meters. First the reds fade, then oranges, then yellows, until only blue remains. And below a few hundred meters, even blue vanishes. What remains is darkness almost absolute, broken not by stars but by creatures generating their own faint light, or the glow of an occasional lamp carried by a machine. This difference makes the two kinds of darkness profoundly different to human perception. Space's darkness inspires wonder. It tempts us to gaze longer, searching for more detail, feeling the expanse of the universe. The ocean's darkness often inspires unease. It feels enclosing, pressing close, hiding things we can't see. In space, darkness is distance. In the ocean, darkness is concealment. Both affect us deeply, though in opposite ways. Darkness in space is more complicated than it first appears. Step into the sunlight in orbit and the black sky doesn't vanish. The stars fade, drowned out by brightness, but the background remains a void. Astronauts on the moon spoke of standing in daylight while still seeing a sky black as ink above them. Without an atmosphere, there's no scattering of blue, no soft diffusion of sunlight across the horizon. The sky is always dark, no matter the time. That contrast, bright surface, black sky, can be unsettling. It's a reminder that even in light, space is surrounded by emptiness. The ocean, by contrast, creates its own twilight before surrendering to black. The surface dazzles with reflection, but just beneath it, light bends and scatters, making strange shifting patterns. Descend deeper, and the world dims. At 100 meters, sunlight is weak. At 200, it is gone. The gradual fading gives way to sudden absence. Unlike space, where stars always give you something to see, the sea at depth offers nothing to the naked eye. Only artificial lamps or the glow of bioluminescent life puncture the blackness. It's remarkable to think of how quickly this transition happens. Light that travelled across millions of years from stars can still be seen in space. Yet in the ocean, light from our own sun barely penetrates a fraction of its depth. In that sense, the ocean is more effective at hiding itself than space is. The stars reveal the universe. The water hides its secrets. The psychological effect of this matters as much as the physics. Astronauts often describe the view of Earth against the blackness of space as breathtaking, a perspective that brings peace even in its enormity. Divers and submersible pilots often describe the blackness of the deep as unsettling, even oppressive. It's not just that we fear what we can't see, though that's part of it. It's also that the ocean hides things we know are there. Creatures, landscapes, currents, all close, all invisible. Space's darkness is empty. The ocean's darkness is crowded. Yet even in this there are similarities. Both environments force humans to carry light with them. A spacecraft or station has windows glowing faintly, panels reflecting sunlight, lamps for astronauts working outside, A submersible carries beams that cut through the water, illuminating only a small patch before vanishing into black. In both cases, explorers live inside tiny bubbles of light surrounded by immensity. The boundary between known and unknown is sharp. You can see what your lamps or windows show, and beyond that there is nothing but darkness. That edge becomes part of the experience. It's where the familiar ends and the unfamiliar begins. Bioluminescence makes the sea's darkness unique. In the midnight zone, where sunlight never reaches, life has evolved to make its own light. Tiny plankton sparkle when disturbed. Fish flash lures from their heads. Squid pulse blue or green as signals. This light is often dim and brief, but it reveals that darkness doesn't mean lifelessness. In fact, the majority of the ocean is alive in this way, filled with creatures that glow in the dark. Astronauts never see this in space. Outside their windows, the stars are fixed, distant, silent. In the sea, lights flicker nearby, sometimes moving, sometimes vanishing in an instant. It creates a sense that the darkness is alive, not empty. There's a historical irony here. Before electricity, sailors used the stars to navigate across oceans. Those same sailors told stories of glowing seas, waves lit by plankton, ships' wakes sparkling at night. The heavens and the waters both gave light in their own ways, though one came from distant fire and the other from living cells. Even today, when submersibles descend, scientists are amazed at how common bioluminescence is. The deeper they go, the more the darkness seems to blink with brief signals of life. In space, the signals come from galaxies millions of light years away. In the sea, they come from animals just meters outside the window. The effect is strangely similar despite the scale difference. In both directions, darkness is never absolute. It is always broken by light, distant or near. Still, the experience of moving into that darkness remains daunting. In orbit, astronauts step out of an airlock and see Earth below, the cosmos above, and their own body floating in between. The blackness stretches forever, but it doesn't threaten directly. In the sea, when the lamps switch off, the blackness presses close, impenetrable, as if the world outside the hull no longer exists. That difference shapes how we talk about the two frontiers. Space is called vast, infinite, endless. The sea is called deep, hidden, unknown. One is open, the other is closed. Darkness also dictates technology. Telescopes in space collect faint light from the most distant galaxies, amplifying signals billions of years old. Sonar in the ocean replaces light entirely, mapping the sea floor with sound because light cannot reach it. The tools we use reveal how darkness changes the very way exploration happens. Above, we build machines to see farther. Below, we build machines to sense without seeing. Our imagination follows the same path. When we picture space, we imagine stars and galaxies. When we picture the sea, we imagine creatures lurking unseen. The irony is that in both cases the darkness is simply a limit of human senses. Light still exists in both places, just not for our eyes. In space, ultraviolet, infrared and radio waves flood the cosmos, invisible until we build detectors. In the sea, pressure waves, chemical signals and magnetic cues guide animals perfectly adapted to the abyss. Darkness, then, is not absence. It is just a mismatch between our biology and the environment. But because we are bound to our own senses, we experience it as frightening, mysterious, or awe-inspiring. What both directions teach us is humility. We rely on technology not just to survive, but to perceive. Without lamps, sensors, or telescopes, the universe would be black in both sky and sea. With them, we discover detail, life, and structure. Every photon from a star, every flicker from a bioluminescent fish is a reminder that darkness is not complete. It only seems that way to us. As we continue exploring the parallels, we see that darkness is just one piece of the challenge. Machines must survive not only what they cannot see, but also what presses against them. Spacecraft must be light and fast to escape gravity. Submersibles must be heavy and strong to resist pressure. In both cases, the hull becomes the dividing line between light and dark, safety and danger, life and death. The next step in understanding why we go further into one realm than the other lies in these machines themselves, how we design them, how they endure, and what they can or cannot do in the face of extreme conditions. When we look at the achievements of exploration in both directions, one theme stands out again and again. Humans don't go into space or into the sea on their own. They go inside machines. The astronaut floats in orbit not because the human body has adapted to vacuum, but because it rides inside a spacecraft. The diver who descends to the trench survives not because lungs and bones are enough, but because a submersible shields them from collapse. These machines are the real explorers. They are fragile, temporary bubbles of Earth carried into environments that would destroy us in seconds. When we compare spacecraft to submersibles, the similarities and differences reveal why one kind of machine has multiplied and advanced while the other remains rare and specialized. The first thing to notice is scale. Spacecraft are designed to be as light as possible. Every kilogram of mass requires more fuel to reach orbit, and fuel itself adds weight, creating a vicious cycle. That's why spacecraft look fragile compared to airplanes or ships. Thin aluminum walls, lightweight insulation, and delicate structures are chosen not because engineers want fragility, but because they need to balance against gravity and rocket power. A submersible is the opposite. Weight is not a penalty. In fact, weight helps it sink. What matters is strength. A submersible's core is usually a thick sphere of metal, often titanium, designed to resist thousands of tons of pressure. The walls may be many inches thick, making the vessel small inside and heavy overall. Where spacecraft are light shells containing air, submersibles are dense shells resisting water. This shapes the way both machines look. Spacecraft often have flat panels, wings, long trusses, and solar arrays. They spread out like insects, light and delicate with appendages for gathering energy or communicating with Earth. Submersibles, by contrast, are compact, with rounded shapes and minimal protrusions, because anything extending outward becomes a weakness under pressure. One is designed to expand, the other to resist. One stretches outward, the other curls inward. The environments shape every detail. In orbit, temperature extremes demand reflective surfaces, radiators, and insulation. Electronics must be shielded from radiation and micrometeoroids that could puncture them at speeds faster than bullets. In the sea, temperature demands heaters for instruments, seals that prevent leaks, and hulls that can endure constant pressure. Instead of radiation, submersibles face corrosion from salt water, biofouling from organisms, and the risk of entanglement in currents or debris. Both machines are exposed to constant threats, but from completely different sources. Fragility comes from the thin margin between safety and disaster. A spacecraft, if punctured, may lose air too quickly for its crew to survive. A submersible, if its hull fails, will implode in a fraction of a second. The scale is different, but the stakes are the same. That fragility forces engineers to design with extreme caution. Safety margins are tested, simulations are run, and prototypes are built again and again. Even so, accidents happen. The history of both spaceflight and deep-sea exploration includes tragedies that remind us of the risks. Challenger and Columbia in space, accidents with submersibles and diving systems in the sea. Each loss reinforces how unforgiving these environments are. Another difference is how machines move once they arrive. A spacecraft in orbit can circle Earth with almost no fuel, gliding effortlessly thanks to inertia. Maneuvering requires only small bursts from thrusters. A submersible, however, must constantly push against water's resistance. Moving forward, turning, or holding position requires continuous energy. Propellers or thrusters must fight the density of the medium. The ocean doesn't allow effortless motion. That makes deep-sea missions slower and more energy-intensive than space missions of similar duration. Energy itself highlights another contrast. Spacecraft often rely on solar panels, spreading wide arrays to capture sunlight that flows freely in orbit. Even probes travelling to distant planets carry panels or nuclear generators to provide steady power. Submersibles cannot use sunlight. Once below a few hundred meters, solar energy disappears. They rely on batteries or cables for every system: life support, lights, cameras, propulsion. Limited energy means limited time. This, more than almost anything else, keeps submersible dives short and infrequent. Communication adds another layer. A spacecraft can beam signals directly to Earth at the speed of light, passing through the vacuum with little interference. A submersible cannot. Radio waves are absorbed by water within meters. Signals must travel by acoustic methods, which are slower, weaker, and easily distorted. In many cases, a submersible is essentially silent once it descends, recording data for retrieval only when it resurfaces. This makes control difficult, increasing risk and reducing flexibility. In space, ground control can talk to astronauts in real time. In the deep, crews may be alone or connected only through unreliable signals. That isolation shapes the missions, making them slower, more deliberate, and more constrained. It's also worth thinking about how each type of machine ages. Satellites in orbit can last years, even decades, slowly drifting when their fuel runs out. Telescopes can operate for decades until their instruments degrade. Space stations can be repaired and expanded. Submersibles, however, suffer constant wear from pressure, salt, and mechanical stress. Every dive adds fatigue to the hull, every joint must be checked for leaks, and every instrument faces the corrosive nature of seawater. Maintenance is intensive, lifespan is short. That fragility in operation explains why so few deep-diving machines exist compared to spacecraft. Yet both kinds of machines share the same underlying philosophy. They are Earth environments in miniature, carrying air, warmth, pressure, and life support systems into places where none of those exist naturally. They are tiny bubbles of habitability floating in vast hostility. When an astronaut looks at their capsule, or when a submersible pilot looks at their viewport, the awareness is the same. This fragile shell is the only thing separating life from death. That realization shapes how explorers describe their journeys. They don't speak only of the beauty of stars or strange creatures of the abyss. They speak of the machines, the noise of pumps, the feel of air systems, the constant awareness of the thin line of protection. There's also a social difference. Spacecraft are built by massive teams, funded by governments or large corporations, watched by millions during launches. Submersibles are often built by smaller teams, used by niche groups of scientists, and rarely make headlines. One kind of machine becomes a symbol of progress, the other a tool for specialists. This difference in visibility matters. It's one reason space captures imagination while the deep sea remains in shadow. Still, both kinds of machines show human ingenuity at its finest. Consider the International Space Station, a construction the size of a football field orbiting hundreds of kilometers above Earth, assembled piece by piece over years, functioning as both laboratory and home. Then consider Alvin, a submersible that has dived thousands of times, carrying scientists to hydrothermal vents, shipwrecks, and undersea mountains, returning with knowledge that has transformed biology and geology. Both are fragile, both exist in environments we cannot endure alone, and both stand as proof that machines are extensions of human curiosity. The fragility, in the end, is not weakness but reality. Nature did not design humans for vacuum or for crushing depths. Machines bridge that gap. They're fragile because we are fragile. They fail because environments are hostile. But without them, there would be no footprints on the moon, no images of galaxies, no samples from deep-sea vents, No glimpses of giant squid in their natural habitat. The machines take the risks we cannot. They extend our senses where our bodies cannot follow. As we move forward, it becomes clear that machines alone do not tell the story. They carry people, and the people themselves endure stresses as much psychological as physical. Astronauts confined to capsules for weeks, aquanauts sealed inside submersibles for hours, both live with isolation, pressure, and dependence on technology. Their experiences shape how exploration is remembered, celebrated, and pursued, and to understand why one path has been taken so much more than the other, we must turn from the machines to the humans inside them, fragile in their own ways, yet willing to risk everything for the sake of discovery. For all the machines we design, for all the engineering we admire, in the end it always comes back to the people inside. The machines are extensions of us, carrying our fragile bodies into places where we were never meant to survive. Astronauts and aquanauts live parallel lives in this sense, each surrounded by technology that keeps them alive, each confronting an environment that would kill them in moments if anything went wrong. When you compare the two, the differences between space and sea become even clearer, not just in terms of physical challenges but also in psychology, training, and how the rest of the world sees them. The first thing to recognise is just how narrow the margin is for survival. A human being is built for 1 atmosphere of pressure, 21% oxygen, moderate temperature, and gravity pulling constantly downward at 1 g. Remove any one of these, and the body begins to fail. In orbit, gravity becomes microgravity. Oxygen must be carried artificially, and pressure must be sealed inside a capsule or suit. In the sea, pressure multiplies until it becomes unbearable. Oxygen behaves differently under compression, and temperature falls close to freezing. In both cases, the human body is not just out of place, it is actively under threat. Astronauts and aquanauts are trained not to forget this for a single second. Astronauts face challenges that sound almost abstract until you consider them closely. Microgravity changes everything from how blood flows to how bones and muscles stay strong. Without constant loading, bones lose calcium, becoming weaker. Muscles atrophy because they don't have to carry weight. Fluids shift upward, causing swelling in the face and pressure in the eyes, sometimes damaging vision permanently. The immune system alters, sleep cycles are disrupted, and the body adapts in ways that are not always beneficial. To counter these changes, astronauts must exercise for hours each day, tethered to treadmills or pedaling on stationary bikes. What feels like an adventure from the outside becomes a daily routine of discipline just to keep the body functional. Aquanauts, by contrast, don't face microgravity. They remain in the pull of Earth, seated or floating inside submersibles or diving in suits. Their challenge comes from pressure and confinement. A long dive means hours in a cramped sphere, barely enough room to stretch, with only a few companions or sometimes no one at all. The sound of pumps, the creak of the hull, and the knowledge of kilometres of water overhead weigh on the mind. Divers who work at depth also face physiological risks like nitrogen narcosis, decompression sickness, and oxygen toxicity. They train to control panic, to keep breathing steady even when instincts scream to rise quickly. The mental challenge of resisting those instincts is as critical as any machine. Psychology plays a huge role in both arenas. Astronauts often speak of isolation in orbit, being far from Earth, separated by distance and silence. But they also describe the view of Earth as profoundly moving, a constant reminder that home is beautiful and fragile. Aquanauts, meanwhile, cannot see Earth from above. They see only darkness outside their small windows. The isolation feels different, less expansive, more enclosed. Astronauts describe awe. Aquanauts describe intensity. Both know they are in places few others have gone, but the emotional tone differs. The training required to prepare humans for each role reflects these differences. Astronauts train in simulators, aircraft that produce brief moments of weightlessness, and enormous pools where they practice spacewalks underwater. They learn not only technical skills but also how to remain calm in emergencies, to work as a team in confined quarters, and to repair systems under stress. Aquanauts train in diving physiology, emergency procedures, and the discipline of slow ascent. They too use pools, but their focus is on adapting to pressure, managing breathing, and resisting panic. Both forms of training emphasize control over instinct, because instinct in hostile environments is usually fatal. There is also a stark difference in how the world views these two types of explorers. Astronauts are celebrated as heroes, their names remembered by generations. Their missions are broadcast live, their steps onto new worlds replayed endlessly. Aquanauts, despite facing equally dangerous conditions, rarely achieve such recognition. Few people outside scientific circles know the names of deep-sea pioneers. The public attention, the prestige, the cultural weight, these have gone upward, not downward. The imbalance isn't fair, but it shapes how resources are allocated and how many opportunities each group receives. Despite this, both astronauts and aquanauts share common experiences that bind them together. Both describe the constant hum or hiss of life support systems, the sound that reminds them they're alive. Both speak of the importance of crew cohesion, how living in tight quarters with a handful of people creates bonds as well as tensions. Both must endure the long anticipation before launch or descent, knowing that once the hatch closes, the outside world is cut off. Both feel the relief when they return safely, stepping onto solid ground, breathing unfiltered air, feeling sunlight again. Health risks extend beyond the missions themselves. Astronauts returning from orbit often need weeks to regain muscle strength and bone density. Their balance is disturbed, their blood distribution must readjust to gravity. Aquanauts emerging from saturation dives may need hours or days to decompress safely, living in pressurized chambers while gases leave their blood. The journey doesn't end when they step out of the machine. The body continues to adapt and recover, a reminder that the environments they entered left lasting marks. One fascinating aspect is how each group perceives time. Astronauts in orbit see 16 sunrises and sunsets each day as the station circles Earth. Their sense of day and night must be imposed artificially with schedules and lighting. Aquanauts in the deep sea see no sunlight at all. Their time is measured by instruments, clocks, and the rhythm of their tasks. In both cases, natural cues vanish. Time becomes artificial, constructed by technology as much as environment. Living without sunrise or sunset is an experience few humans ever know, and it shapes the way explorers remember their journeys. The fragility of humans in these environments also leads to reliance on remote machines. Satellites, probes, and remotely operated vehicles often take the place of humans because they remove the need for fragile bodies. And yet, there remains something irreplaceable about having people present. Astronauts can repair, improvise, and observe in ways machines cannot. Aquanauts can collect, react, and describe experiences that cameras alone miss. The fragility of humans is also their strength, the ability to adapt, to feel, to perceive in ways that algorithms cannot. That's why, despite the risks, humans continue to go themselves. The comparison also highlights why humanity has invested more in astronauts than aquanauts. The symbolic value of sending people into space, overcoming distance and gravity, resonated deeply with culture and politics. Aquanauts, though equally brave, have rarely been seen as symbols of progress. Their fragility is the same, but the world assigns different meanings to it. Understanding this helps explain why resources flowed upward rather than downward. Yet when you listen to the stories of those who have gone, the parallels outweigh the differences. Astronauts describe silence, isolation, the awareness of fragility, the sound of their own breath. Aquanauts describe the same. Astronauts describe looking out windows and seeing beauty mixed with danger. Aquanauts describe the same, Both know they have carried human presence into places where it does not belong, and both know that without constant vigilance, the environment would reclaim them instantly. The reality is that humans themselves are the most fragile part of any mission. Machines can be rebuilt, reinforced, replaced. Bodies cannot. That fragility defines exploration in both directions, and it's why the next part of the story turns toward the cost of curiosity. Sending fragile humans upward has been funded and celebrated at vast expense. Sending fragile humans downward has been comparatively neglected. Both reveal as much about our values as about our capabilities. When we look at how far we've gone into space compared to how far we've gone into the sea, one explanation stands out above almost all others: money. Exploration, in any form, is not just about dreams or courage, it's about resources. Building rockets, capsules, satellites, and stations takes enormous investment. Building submersibles, sonar networks, and undersea labs also takes investment. But the difference lies in how those costs have been valued by governments, by industries, and by the public. For decades, money has poured into the sky, while the ocean has received only fragments of that attention. The imbalance is so extreme that it's not just a matter of numbers, it reflects priorities, culture, and what we choose to see as meaningful. Consider the budgets of space programs. During the Apollo era in the 1960s, NASA consumed about 4% of the entire United States federal budget. That translated into billions of dollars each year, at a time when billions carried even more weight than they do today. The Soviet Union matched that effort with its own massive investments, pouring money into launch systems, cosmonaut training, and satellite technology. These sums were not spent because of pure curiosity. They were spent because of competition, because space became a stage for global rivalry. To land on the moon was to prove power, capability, and dominance. In such an atmosphere, money flowed almost without question. The ocean, in contrast, never became a battlefield of prestige. There were naval programs, of course, with submarines patrolling quietly under the seas, but those efforts were military, not scientific. Oceanography, deep-sea biology, and undersea geology never received funding on the scale of rockets or telescopes. Even today, the entire budget for deep ocean science in the United States is a fraction of what NASA receives annually. Global comparisons tell the same story. Billions are spent to launch satellites, to plan Mars missions, to build new telescopes, while only modest sums fund the vessels and instruments needed to map the seafloor or study deep ecosystems. The irony is clear. The ocean directly sustains life on Earth. It regulates climate, drives weather, produces much of the oxygen we breathe, and feeds billions of people. Space exploration inspires us, but the ocean supports us. Yet funding flows toward the stars. Why? The answer is complicated, tied to culture, politics, and perception. Space carries symbolism. To go to space is to go beyond, to escape Earth, to show human ambition reaching upward. The ocean feels local, domestic, even though it covers most of the planet. The difference in perception has enormous consequences for how resources are allocated. Part of the explanation also lies in visibility. A rocket launch is spectacular. Flames, smoke, countdowns, cheers, images that can be broadcast worldwide, stirring emotion in millions of people. A submersible dive, by contrast, happens quietly, far out at sea, with only a handful of people involved. There is no crowd, no countdown, no dramatic liftoff. The event may produce stunning scientific results, but it rarely produces images that inspire public fascination on the same scale. That lack of spectacle makes it harder to rally funding, harder to generate urgency. This isn't to say the ocean has been ignored completely. Institutions like the Woods Hole, Oceanographic Institution, the Scripps Institution of Oceanography, and national programs in countries like Japan and France have built submersibles, operated research vessels, and supported decades of study. Discoveries of hydrothermal vents, deep-sea creatures, and undersea geology have all come from these investments. But the budgets remain tiny compared to space. Often the annual funding for ocean science is less than the cost of a single rocket launch. It's not that the ocean is cheap to explore, it's that we've chosen not to spend on it. Commercial interests also play a role. Satellites provide immediate, profitable services: communication, navigation, weather forecasting, Earth observation. Billions of dollars are earned by industries that depend on satellites, creating strong incentives to fund launches. Deep-sea science, by contrast, generates knowledge but not immediate profit. Industries that use the ocean, fishing, shipping, energy, spend money, but they don't prioritize fundamental exploration. They want resources, not knowledge. This difference in economic payoff explains why so much private investment flows upward instead of downward. Even when private individuals have stepped into ocean exploration, it has been rare and sporadic. James Cameron funded his own dive to the Challenger Deep in 2012, producing valuable science and imagery, but it was a one-time event. A handful of wealthy entrepreneurs have begun investing in undersea vehicles, but nothing on the scale of private space companies like SpaceX or Blue Origin. In the eyes of investors, the sky promises returns, while the sea promises mystery with little profit. Another factor is political narrative. Presidents and prime ministers can point to rockets as symbols of progress, uniting nations in pride. They can stand at a podium and declare that their country will reach the moon or Mars, and the world listens. It is harder to stand at a podium and declare that the country will map the ocean floor, even though such a goal might be equally ambitious and far more useful. The difference is not rational, it's emotional. Leaders respond to what captures imagination, and space has always done that more than sea. Yet the cost imbalance carries consequences. Because the ocean is less explored, we are blind to many of the changes happening there. Climate change, acidification, species loss and pollution are reshaping marine ecosystems, often faster than we can study them. Billions spent on satellites give us incredible detail about the surface of Earth. Yet we know more about the geology of Mars than about the geology of our own seabed. This ignorance is not due to impossibility, it is due to neglect. The money has not been spent, the missions not prioritized. The cost of curiosity has been measured differently in each direction. It's striking to think of what might have been if even a fraction of the money spent on space had been directed to the ocean. We might already have detailed maps of every trench and ridge, catalogues of countless undiscovered species, and permanent laboratories on the seafloor. Instead, progress has been slow, uneven, and largely invisible to the public. Curiosity about the sea exists, but curiosity without funding remains just that, curiosity. Still, it's not fair to say that space exploration wasted its billions. Satellites, telescopes, and missions have transformed science, communication, and even daily life. Weather forecasts, GPS, disaster monitoring, all of these come from space technology. The point is not that space deserved less, but that the ocean deserved more. Humanity could have balanced its curiosity, investing upward and downward together. Instead, one side flourished while the other languished. The phrase, billions for the stars, pennies for the sea, is not exaggeration. Global space budgets today add up to tens of billions each year, with single projects like the James Webb Space Telescope costing over $10 billion alone. Meanwhile, international ocean exploration efforts scrape by with budgets in the tens or hundreds of millions. The difference is an order of magnitude, not a small gap. That gap explains why we have high-resolution images of distant galaxies, but no comparable maps of Earth's own seabed. In the long run, this imbalance raises important questions about priorities. Do we pursue exploration mainly for inspiration, for prestige, for symbols? Or do we pursue it for practical knowledge, for the health of the planet that sustains us? The answer has always been a mix, but the weight has tilted heavily toward inspiration. That tilt explains why the sky has been opened while the sea remains closed. As we think about what this means, it's worth remembering that cost is not just measured in money, it is also measured in opportunity. Every billion spent in one direction is a billion not spent in the other. By choosing the stars over the sea, we have learned much about the universe, but left much of Earth's own mystery untouched. That trade-off may not be permanent, it may shift in the future. But so far it has defined our age of exploration. And as we move on, we see how cost links directly to communication. The value of satellites comes partly from how they connect us instantly across continents. The weakness of submersibles comes partly from how little they can communicate while submerged. Communication, like cost, shapes exploration, dictating where resources flow and where curiosity lingers but goes unfunded. One of the great dividing lines between space and sea is how easily or how poorly we can communicate across them. In the modern world, communication feels almost invisible, taken for granted. A phone call reaches across oceans instantly. A video stream moves from one continent to another in real time. Messages and images bounce through the air without delay. But this ease is not universal. It is the product of space technology above our heads and the physics of how signals behave in different environments. Space has turned out to be remarkably open to communication. The sea, by contrast, is almost hostile to it. That difference has played as large a role as any in deciding where humanity has gone further. Electromagnetic signals, radio waves, microwaves, light, move freely through the vacuum of space. There is nothing to scatter or absorb them. A spacecraft can send a radio signal across hundreds of thousands of kilometers, and though the strength diminishes, the message still arrives. That's why we can talk to astronauts in orbit almost instantly, hear their voices with only a fraction of a second's delay. It's why we can still receive faint whispers from probes like Voyager, decades after they left Earth, travelling billions of kilometers away. In space, communication is limited only by distance and power, not by the medium itself. The ocean could not be more different. Water absorbs and scatters electromagnetic wave quickly. Radio signals that travel effortlessly through air die within a few meters underwater. Even very low-frequency waves, which penetrate further, require enormous antennas and still struggle to go beyond modest depths. Light too disappears rapidly. A lamp or laser can travel only a short distance before fading into darkness. What this means in practice is that once a submersible descends, it becomes almost silent to the outside world. Communication is reduced to acoustic methods, sound waves transmitted through the water. Sound travels well in the sea, far better than light or radio, but it comes with limitations. It moves slower than electromagnetic waves, creating delays. It is distorted by temperature, salinity, and currents, bending and scattering as it passes through layers of water. The deeper the submersible, the more challenging it becomes to send a clear signal to the surface. Bandwidth is also limited. Where satellites can beam down gigabytes of data per second, a deep-sea acoustic link may struggle to carry more than a few simple signals. Streaming live video from the bottom of the ocean remains almost impossible. Scientists often record data on board and wait until the vessel resurfaces to retrieve it. This divide in communication capability has enormous consequences for exploration. Space missions can be followed in real time. The entire world watched the Apollo astronauts step onto the moon because signals travelled back instantly. Even robotic missions to Mars send images daily, giving the public a sense of participation. The sea offers no such immediacy. A dive may last hours or days, but the world only sees the results after the fact. That lack of spectacle makes it harder to generate excitement, harder to capture imagination, and harder to justify large budgets. Communication, or the lack of it, shapes perception as much as discovery. The difference also affects safety. Astronauts are monitored constantly by mission control. Every heartbeat, every word, every system reading is tracked on the ground. Problems can be spotted instantly, solutions proposed, decisions made with the full support of a team. Submersible crews do not have that luxury. At best, they may maintain patchy contact through acoustic pings, enough to send simple status updates but not enough for detailed troubleshooting. If something goes wrong in the depths, the crew must solve it themselves. That isolation adds another layer of risk, and another reason why fewer people have gone deep compared to those who have gone high. Satellites add to the contrast. Orbiting above Earth, they serve as relays, bouncing signals across continents. They knit the planet together with instant communication, guiding airplanes, ships, and phones alike. Nothing equivalent exists below the sea. There are no networks of undersea satellites, no systems that allow continuous real-time contact with submersibles. Fibre optic cables do cross oceans, carrying much of the world's internet traffic. But these are fixed lines, not tools for mobile exploration. The idea of building a global communication system for the deep sea has been raised, but the costs and technical challenges are enormous. Until then, saltwater silence remains the rule. The irony is striking. Space, which seems so distant, is actually easier to connect to than the depths just below us. We can hold a video call with astronauts on the International Space Station circling Earth at 28,000 kilometers per hour. Yet we cannot watch in real time what lies a few kilometers beneath the waves. We can send commands to a rover on Mars and receive images back the same day, but we cannot steer a deep-sea vehicle with the same immediacy. The physics of communication has made space more accessible than sea, even though one lies beyond the sky and the other lies right here on our planet. For humans inside these machines, the experience of communication shapes their state of mind. Astronauts, though far from home, hear voices from mission control, speak to family, and know they are being watched over at every moment. Aquanauts, in contrast, often know they are alone. Even when a faint link exists, delays and distortions mean conversations are limited. The psychological weight of silence is heavy. The sea isolates in ways space does not. That isolation is part of why fewer are willing to fund, support, or even attempt long-term missions underwater. Technology may shift this in the future. Advances in acoustic systems, autonomous robots, and tethered fibre lines may allow better contact with the deep. But for now, silence defines the abyss. Every dive is not only a journey into darkness, but also a journey into disconnection. That disconnection explains why deep-sea missions remain rare, short, and limited in scale. Communication, as much as pressure or temperature, is a barrier. When you step back and compare, the divide becomes clear. Space welcomes signals but resists bodies. The sea resists signals but welcomes life. That balance may be the single most important reason why we know more about the universe above than the ocean below. We can send sensors to the stars and still talk to them. We send sensors to the sea and they fall silent. The story of exploration has always depended not just on where we go, but on how we tell others about it. Space tells its story instantly. The sea keeps its secrets until the mission is done. This gap in communication also sets the stage for how we map, record, and understand each environment. In the case of space, real-time data allows us to build detailed maps of planets, moons, and galaxies. In the case of the sea, mapping depends on slower methods, sonar sweeps, and indirect measurements. What we know about the cosmos comes to us almost as it happens. What we know about the ocean comes to us long after the fact. The difference isn't curiosity, it's connection. As the story continues, this divide in communication naturally leads to the question of mapping. If satellites and telescopes give us precise images of worlds far away, why do we still lack detailed maps of our own sea floor? The answer lies not only in money, but also in how signals behave, how tools are limited, and how physics sets boundaries. The silence of the sea has kept its geography hidden far longer than the stars. To understand why, we must look more closely at how we've tried to chart both the universe above and the ocean floor below. For as long as humans have been curious about the world, maps have been one of our main tools to make sense of it. A map is more than a drawing. It's a way of turning mystery into knowledge, of replacing uncertainty with structure. Long before rockets or submersibles, people mapped coastlines, rivers and mountain ranges, trying to impose order on landscapes that seemed endless. When we speak of space or sea, we often forget that exploration is not just about going there. It's about recording what we find, charting the unknown so that it becomes part of the known. The contrast between how we've mapped the universe and how we've mapped the ocean floor reveals another reason why we know more about the stars above than the waters below. When astronomers look up at the night sky, they are not seeing random points. They are looking at data that can be measured and organised. With telescopes, we capture light from stars, galaxies, and planets. We measure positions, brightness, movement, and composition. Over centuries, this has created charts of astonishing precision. We know the layout of constellations, the distances to nearby stars, even the structure of galaxies millions of light years away. Satellites and space telescopes now add layers of detail, mapping the microwave background of the universe, charting exoplanets orbiting distant suns, and even building three-dimensional models of stellar neighbourhoods. In short, our maps of the universe, while still incomplete, stretch to unimaginable scales. The ocean floor, by comparison, remains largely a blank space. Even today, with sonar, satellites and advanced instruments, only a small percentage of the seabed has been mapped in high detail. Vast regions are known only in outline. Trenches, ridges, seamounts and plains exist on charts, but often with rough resolution. In some areas, our maps are so vague that features the size of mountains could remain undiscovered. The irony is hard to ignore. We have detailed charts of the surfaces of Mars, the Moon, and even some moons of Jupiter and Saturn, yet our own planet's sea floor remains a patchwork of unknowns. Why this difference? The physics of observation plays a major role. Light travels freely through space, carrying information from distant objects to our telescopes. We can capture it, analyse it, and turn it into maps. The sea blocks light almost entirely. Once below a few hundred metres, sunlight vanishes. Satellites cannot see the bottom through kilometres of water. Instead, mapping must rely on sound, sonar pulses sent downward, bouncing off the seafloor and returning with echoes. This method is powerful but limited. It builds maps slowly, sweep by sweep, requiring ships to travel back and forth across the ocean like a painter covering a canvas. At current rates, completing a full high-resolution map of the seafloor could take decades or longer. Satellites have helped somewhat by measuring tiny variations in sea surface height caused by gravity. A seamount below, for example, pulls slightly more water above it, creating a subtle bulge detectable from orbit. Using this technique, scientists have built global maps of seafloor features with rough resolution, but rough is not enough. A ridge may be outlined, but its detailed structure remains hidden. A trench may be identified, but its exact depth remains uncertain. To truly know the seabed, we must go directly, with sonar from ships or autonomous vehicles. That requires time, money and effort, resources that have rarely matched those given to space telescopes. The cultural weight of maps matters too. Charts of the stars have always inspired stories. Constellations became myths. Navigators guided ships by the stars, and astronomers presented maps as glimpses into cosmic order. Seafloor charts, by contrast, have rarely captured the public imagination. A map of a trench does not stir the same excitement as a map of a galaxy. The sea is seen as utility, the sky as wonder. That difference affects not just curiosity, but also how much we are willing to invest in turning blank spaces into detailed knowledge. Yet the ocean floor holds mysteries just as profound as those of the stars. Hydrothermal vents, discovered only in the late 20th century, revealed ecosystems that thrive without sunlight, powered by chemistry instead of photosynthesis. Seamounts host unique species found nowhere else. Submarine canyons cut through continental margins in shapes as dramatic as any mountain range on land. Each feature carries information about Earth's geology, climate history, and even potential resources. To map the ocean is not simply to satisfy curiosity, it is to understand the system that regulates life on this planet. Think of how mapping has changed our relationship with space. The first telescopic charts transformed vague points of light into moons orbiting Jupiter, craters on the Moon, and rings around Saturn. Each map expanded our sense of place. Ocean mapping could do the same, showing us how interconnected Earth truly is, how currents, ridges, and trenches shape the atmosphere, the climate, and life itself. The absence of maps leaves us blind to changes already underway, from rising seas to shifting ecosystems. Another important point is accessibility. Anyone with a telescope, even a small one, can take part in mapping the sky. Amateur astronomers contribute to discoveries, track asteroids, and refine charts. The sea offers no such democratization. Mapping the ocean floor requires ships, sonar, and expensive equipment. It cannot be done from a backyard or a balcony. That exclusivity slows progress, concentrating exploration in the hands of a few institutions. In space, curiosity spreads widely. In the sea, it remains concentrated. The irony deepens when we realize that some of the best seafloor maps come not from scientific missions, but from the search for lost aircraft and ships. The hunt for Malaysia Airlines. Flight 370, for example, generated detailed charts of parts of the Indian Ocean that had never been mapped before. A tragedy, not curiosity, pushed investment. Space exploration, on the other hand, is driven largely by vision, by goals set openly for discovery. The contrast says much about what drives mapping in each direction. Still, progress is being made. International efforts like Seabed 2030 aim to map the entire ocean floor by mid-century. Advances in autonomous vehicles may speed the process, allowing fleets of robots to survey vast areas. As with space telescopes, collaboration and technology may eventually close the gap. But for now, the difference is stark. We can chart galaxies billions of light years away, yet large parts of our own planet remain as blank as they were on maps centuries ago. The comparison between universe charts and ocean floor mysteries leads to a sobering realization. We don't know less about the sea because it's less important. We know less because the tools are harder, the costs are neglected, and the culture has not demanded it. Space offers light and distance, which our telescopes can harness. The sea offers darkness and obstruction, which demand effort and patience. One opens itself to mapping, the other hides. Yet both pursuits, when successful, reveal something profound. To map is to transform the unknown into knowledge, the blank into structure. It is to replace myth with measurement, uncertainty with understanding. The night sky and the seabed alike challenge us to do this. We have risen to one more than the other, but the potential of both remains vast. And as we move on, the story of mapping leads naturally into the story of what we find when maps are made. In the case of space, maps reveal planets, moons, and galaxies. In the case of the sea, maps reveal creatures so strange they might as well be from another world. The next step in our journey takes us from charts to life itself, from the outlines of mystery to the living beings that inhabit it. When people talk about aliens, they usually imagine spacecraft arriving from another star, beings stepping out with strange shapes, new biology, and motives we can't understand. Science fiction fills our imagination with them, but in truth, the closest thing to aliens we've ever encountered are not in the sky above. They live here, in the deep sea. For centuries we barely knew they existed. The surface of the ocean hinted at life, fish, whales, and creatures close enough to our world that we could catch, study, and eat them. But below a few hundred meters, where sunlight disappears, the forms of life shift into something so strange that they truly feel like emissaries from another planet. It's worth remembering that until the late 19th century, many scientists assumed nothing lived in the deep ocean. The absence of light, the crushing pressure, the cold, all seemed incompatible with life. When nets and dredges were lowered into deep waters and brought back strange creatures, it shocked the scientific community. Fragile gelatinous animals, fish with enormous eyes or none at all, bodies transparent or glowing. The discoveries overturned assumptions. Life did not vanish with light. It flourished in ways that defied expectations. Take bioluminescence, for example. In the deep sea, light is produced by life itself. Tiny organisms glow when disturbed, making waves sparkle at night. Larger animals carry their own lanterns, glowing organs powered by chemical reactions. Some, like the anglerfish, use this light as a lure, dangling it in front of their enormous mouths to draw in prey. Others use it to communicate, flashing signals to mates or rivals. Still others use it defensively, exploding into sudden brightness to startle predators. Imagine walking through a forest at night where every tree, insect and bird glowed with its own light. That's the reality of the ocean's midnight zone, where life itself fills the role of stars. The variety of forms is staggering. Some fish have jaws that unhinge so wide they can swallow prey larger than themselves, an adaptation to scarcity in the depths. Others have bodies mostly made of water, delicate and nearly invisible, drifting like ghosts. Squids grow to enormous sizes, their tentacles stretching longer than buses, eyes the size of dinner plates. Jellyfish pulse silently, some trailing filaments that extend meters behind them. Crustaceans, worms, and countless other creatures have adapted to pressure and darkness in ways no land animal could survive. Each discovery feels like encountering something wholly other, something beyond human imagination. One of the most remarkable examples came with the discovery of hydrothermal vent ecosystems in the 1970s. At depths where no sunlight reaches, vents spew mineral-rich water heated by Earth's interior. Around these vents, entire communities thrive. Giant tube worms, clams, crabs, and fish, all surviving not through photosynthesis but through chemosynthesis. Microbes convert chemicals from the vents into energy, forming the base of a food chain independent of the sun. This was revolutionary. For the first time, scientists realized life could exist without sunlight at all. The implication extended beyond Earth. If life can thrive around vents in our ocean, perhaps it can thrive in similar environments on icy moons like Europa or Enceladus, where oceans lie beneath frozen crusts. The deep sea showed us not just strange life, but new possibilities for life everywhere. The more we explore, the more alien the creatures become. Some fish produce antifreeze proteins to keep their blood from freezing. Others collapse if brought to the surface because their bodies are adapted only to high pressure. Many remain undescribed, caught only in fleeting glimpses by cameras before vanishing into darkness. Entire ecosystems remain beyond our knowledge, waiting in trenches, canyons, and ridges unmapped. Every dive seems to bring new forms. Scientists often joke that it's hard to lower a net into deep waters without pulling up a species no one has seen before. These creatures also defy our sense of scale. Some are microscopic, drifting invisibly in the water, while others, like the colossal squid, grow to sizes that rival whales. Some glow faintly, others flash like strobe lights. Some live solitary lives, others gather in enormous swarms. The diversity is greater than most people realize, and yet our picture is still incomplete. We've explored only a fraction of the deep sea, which means the majority of species remain unknown. It's not unreasonable to say the ocean holds millions of aliens we have yet to meet. The adaptations themselves highlight creativity and evolution. In space, we imagine aliens with traits suited to harsh conditions, bodies resistant to radiation, ways to survive without air. The deep sea provides real examples. Fish with transparent heads that can look upward through their own skulls. creatures that generate red light invisible to most others to hunt unseen, animals that live for centuries, growing slowly in the cold, even simple shrimp display strategies that seem fantastical. Some can snap their claws so fast they create bubbles hotter than the surface of the sun, stunning prey with shock waves. These aren't exaggerations, they're documented realities of the abyss. For humans encountering these beings, the effect is profound. Divers and submersible crews describe feelings of awe and disbelief as if they've stepped into a dream. Looking out a small viewport and seeing a glowing creature drift past, unlike anything seen before, is to be reminded that Earth itself is a kind of alien planet. We live on the surface, but most of the biosphere lies below, in darkness, filled with life that does not resemble us. The notion that we are familiar with Earth is misleading. We are familiar with a small part of it. The rest remains alien. This perspective also shifts how we think about exploration. Astronauts search for signs of life on other planets, often in barren landscapes. Aquanauts find new life forms almost every time they dive, often in abundance. Yet the funding and attention still tilt upward. This imbalance doesn't make sense when you consider the richness of discovery waiting below. Creatures of the deep challenge not only our scientific understanding, but also our imagination. They force us to ask what life means, how it adapts, and what possibilities exist beyond our surface. The parallels between deep-sea creatures and imagined extraterrestrials are striking. Tentacled beings, glowing organisms, giants lurking unseen. These populate both mythology and modern science fiction. But they also populate the real ocean. The difference is that we don't have to wait for a spaceship to bring aliens to us. They're already here, only hidden by kilometers of water. This reality can be unsettling, but it can also be inspiring. We don't need to leave Earth to encounter the bizarre. We need only to look deeper. Despite this, most people never will. Submersibles that carry humans to these depths are rare, and the majority of our knowledge comes from robotic vehicles. Videos and images bring glimpses, but they can't fully convey the scale or strangeness. To see a giant squid in its natural environment, drifting silently through black water, is to witness something almost otherworldly. To see tube worms clustered around vents, glowing faintly in the light of a submersible, is to realize life can take forms beyond imagination. These experiences are rare, and perhaps that rarity is why the deep sea still feels so alien. The creatures of the deep also remind us of our ignorance. For every species described, there are countless more unseen. For every adaptation we understand, there are others we don't. We've catalogued life on land with relative completeness, but in the ocean, we are still at the beginning. It's possible that some of the most extraordinary forms of life on Earth are still unknown, waiting quietly in trenches or ridges we haven't yet explored. That possibility is both humbling and motivating. When we think of aliens, we often ask how they would change our perspective on ourselves. Deep-sea creatures do the same. They show us that Earth is not a single familiar place, but many unfamiliar ones stacked together. They challenge the assumption that life must resemble us, live like us, or depend on the same resources. They prove that adaptation has no single path, that survival finds ways we would never predict. In that sense, they are as profound a discovery as any we might make among the stars. And as the story unfolds, these creatures connect to another theme: resources. The same deep-sea environments that hold alien life also hold minerals, energy, and potential wealth. Just as space exploration is tied to talk of mining asteroids or colonizing planets, ocean exploration is tied to the question of how much we take from these alien ecosystems. Curiosity and utility are entangled. To understand why we choose one path over the other, we must look not only at the beauty of discovery, but also at the promise of resources hidden in the depths. When people dream of exploration, they rarely imagine it as purely scientific. Curiosity may light the spark, but the long fire of investment usually burns only when wealth or resources are involved. Space and sea both carry this double meaning. They're realms of wonder, yes, but also realms of potential utility. We talk about them in terms of survival, inspiration and discovery, but almost always, somewhere beneath those words, the question of riches arises. If we could mine the moon, what could we gain? If we could mine the seabed, what could we take? These questions shape the paths of exploration as much as science ever has. The moon was one of the first places people looked to with resource ambitions. Beyond the symbolism of landing there, its surface hinted at practical materials. Regolith, the dusty soil of the moon, contains metals, oxygen bound in minerals, and rare isotopes like helium-3, which some imagine could be used for future nuclear fusion reactors. The possibility of extracting water ice from craters near the poles adds even more incentive, since water can be split into hydrogen and oxygen for rocket fuel. These ideas are not fantasy. Missions in recent years have confirmed the presence of ice, measured the distribution of elements, and mapped regions that could support future mining. Nations and private companies alike speak of building the infrastructure to harvest lunar resources, arguing that it could support not only local bases, but also deeper ventures into the solar system. Asteroids, too, are included in this vision. Rich in metals like nickel, iron, cobalt, and even precious elements like platinum, they are often described as floating treasure troves. The cost of reaching them is enormous, but the value of their contents, at least on paper, is higher still. Investors have already founded companies dedicated to asteroid mining, even if the technology remains far from realization. The dream of extracting resources from beyond Earth continues to push money, research, and imagination upward. The seabed, however, is another kind of treasure trove, much closer yet far less pursued. Deep in the ocean, at spreading ridges and around hydrothermal vents, lie deposits of metals. Copper, zinc, gold, silver, and rare earth elements accumulate there, carried by superheated fluids that pour from the crust. In vast areas of the deep plains, nodules rich in manganese, nickel, cobalt, and other valuable materials lie scattered like rocks across the seabed. These nodules form slowly over millions of years, layer by layer, as minerals precipitated out of seawater. They are not small resources. They're immense, covering entire regions of ocean floor. If collected, they could supply industries with materials vital for electronics, batteries, and renewable energy technologies. Yet attempts to exploit them have always stumbled. The difficulty of operating at such depths, the cost of retrieving and transporting materials, and the environmental risks have kept deep-sea mining largely theoretical. Pilot projects exist, and some countries have licenses to explore certain seabed regions. But large-scale commercial mining has yet to begin. Environmental concerns weigh heavily. Disturbing deep ecosystems could have consequences we barely understand, wiping out species before they are even discovered, disrupting cycles that affect the entire planet. Unlike the barren moon or asteroids, the seabed is alive, filled with ecosystems we don't yet comprehend. That makes mining there not just a technical issue, but an ethical one. The contrast between mining the moon and mining the sea reflects our cultural attitudes. Extracting from the moon feels clean, futuristic, and far away. Extracting from the sea feels messy, destructive, and close to home. The irony is that the seabed could be reached with far less cost than sending rockets to the moon. The materials are here, within reach, yet the narrative has leaned upward. Investors and governments are more willing to fund visions of lunar or asteroid mining than to confront the environmental debates surrounding the seabed. This is not to say lunar or asteroid mining will be easy. The technical challenges are immense. Building spacecraft capable of landing, drilling, extracting, and transporting material across hundreds of thousands or millions of kilometers. But the prospect of being first, of opening a new frontier, carries allure. In space, the unknown itself is a selling point. In the sea, the unknown is a deterrent. It is remarkable how the same conditions, unmapped terrain, uncertain risks, fragile ecosystems are framed as opportunity in space and as burden in the sea. The economic argument extends beyond resources themselves. Mining the moon or asteroids is often framed as necessary for expanding humanity into the solar system, a step toward becoming a multiplanetary species. Mining the sea, by contrast, is rarely framed in such grand terms. It is seen as industrial, as an extension of extraction already happening on land. That lack of vision, that absence of romance, explains much of the disparity. People will rally behind rockets carrying dreams. They rarely rally behind dredges carrying minerals. Yet the reality is that the sea holds riches that may prove vital in the near future. The demand for metals used in batteries, electronics, and renewable energy is growing rapidly. Land-based sources are limited and often tied to political conflict. The seabed could ease that pressure, providing new supplies for technologies essential to reducing carbon emissions. This creates a tension. The very industries needed for sustainability may drive extraction in one of Earth's last untouched environments. Balancing these needs is one of the greatest challenges ahead. Meanwhile, the moon continues to be promoted as a stepping stone, a place where resources can support further exploration. Water ice there could enable fuel depots for missions to Mars. Regolith could provide construction material for bases. Helium-3, though speculative, is described as a potential energy source for the future. These arguments are not purely about profit. They are about infrastructure, about enabling humanity to move beyond Earth. Mining the sea cannot offer the same narrative. It may sustain industries, but it cannot launch us to new worlds. That difference explains much of the enthusiasm gap. Still, the parallels remain strong. Both the moon and the seabed represent frontiers where resources are abundant but difficult to reach. Both carry risks, technical, financial, and ethical. Both challenge us to weigh short-term gain against long-term consequence. And both reveal that curiosity alone is rarely enough to drive exploration. Money, resources, and opportunity usually tip the scales. The creatures of the deep remind us of what is at stake. Mining the seabed is not like mining a barren asteroid. It means disturbing ecosystems we barely understand, many of which may hold keys to biological innovation or even medicine. The moon holds no such life. That difference may ultimately guide our choices. Exploiting the sea could cost us more than it gives if done recklessly. Exploiting the moon, while technically harder, may avoid those ethical risks. What's clear is that resources are not neutral. They shape how we view frontiers, how we fund them, how we justify them. When we imagine mining the moon, we see a future of expansion. When we imagine mining the sea, we see a present of destruction. Both images are true in part, both incomplete. But together, they show why humanity has turned more eyes upward than downward. The sky promises riches wrapped in dreams. The sea promises riches wrapped in consequences. And yet, when we set aside profit and look again at exploration itself, another parallel emerges. Both realms are treated as metaphors, the sea as space and space as sea. The language of navigation, the frontiers of voyages applies to both. The history of ships crossing oceans inspired the language of rockets crossing voids. The history of submersibles navigating darkness inspired metaphors of space as an ocean. This metaphorical link reveals that while we treat them differently in practice, we see them as connected in imagination. The sea and the stars mirror one another, each reflecting our hunger for discovery. When humans first began to describe what it might mean to leave Earth, they almost always turned to the sea for metaphors. Rockets were called ships. Crews were called sailors of the void. The vacuum was described as an ocean, vast and endless, with currents of gravity and tides of radiation. It made sense because for centuries the greatest unknown on Earth was not land but water. People had crossed continents, climbed mountains, and lived on nearly every surface. But the oceans stretched beyond sight, holding mysteries that felt infinite. To sail across them was to venture into the unknown. When space exploration began, the same language fit perfectly. The sea had been humanity's first frontier. Space was the next. The parallels are everywhere. Think of the word spaceship. It echoes ship, carrying not just the idea of a vehicle, but the weight of a cultural tradition, crews, voyages, expeditions. The command centres of space agencies are called Mission Control, echoing Naval Command. Even the way astronauts describe their time in orbit often leans on seafaring language. Docking is like mooring, modules are like cabins, and the sense of isolation is compared to being far out at sea. The metaphor has shaped how we think, making the unfamiliar cosmos feel slightly more familiar by comparing it to something our history already knew. But the parallels run deeper than words. Both sea and space demand leaving behind the familiar to enter environments that cannot sustain us. Both require vessels that carry not just people but entire worlds of support: air, food, warmth, tools. Both involve risk at every step, with no safety net beyond the machine itself. And both have histories marked by courage, loss, and triumph. When we study one, we see reflections of the other. History reinforces this connection. The age of exploration, when European ships set sail across unknown waters, is often compared to the space age. The motives overlapped: curiosity, trade, prestige, and power. Just as kings and queens once funded voyages to map coasts and claim lands, governments later funded rockets to orbit Earth and claim prestige. Just as sailors once faced storms, starvation, and mutiny, astronauts face technical failures, isolation, and the unknown. Each era was shaped by new technology: compasses and sails in one case, rockets and computers in the other. Each required navigation across vast expanses without certainty of what lay ahead. The sea also provided the literal training ground for space. Astronauts practiced weightlessness in neutral buoyancy tanks, simulating the way their bodies would move without gravity. They trained in submarines to experience confinement. The entire idea of a capsule echoes the tight hulls of early submersibles. Aquanauts living in undersea habitats were studied as analogues for space missions, their isolation and teamwork providing lessons for long-duration flights. Even today, undersea missions like NASA's Nemo project use the sea as a stand-in for space, because the parallels are so strong. There is also the shared psychological experience. Sailors describe the horizon stretching endlessly, the sense of being far from land, with only their vessel and their crewmates as constants. Astronauts describe orbit in almost identical terms: the endless blackness outside, the reliance on their craft, the bond with their crew. Both experiences create a sense of smallness, of being surrounded by vastness, of relying entirely on human ingenuity to survive. In both cases, the environment is not neutral. It is actively hostile. Survival is not natural, it is created. The parallels extend to myths and imagination. Just as ancient sailors told stories of sea monsters lurking in the depths, modern culture imagined alien beings lurking in the stars. Both reflect the same human response to the unknown, to fill it with creatures, fears, and wonders. Both inspire art, literature, and storytelling. The ocean gave us epics of voyages and tempests. Space gives us science fiction, starships, and cosmic battles. The pattern is the same, the setting different. Even the way exploration unfolds feels similar. At first, small missions test the waters, short voyages close to shore, short orbital flights. Then longer journeys push farther, crossing oceans, landing on the moon. Each step builds on the last, requiring new technology, new confidence, and new ambition. The rhythm of exploration repeats itself across centuries, only the environment changing. The sea was the first rehearsal, space is the continuation. There's also the parallel of cost and reward. The first ocean voyages were expensive, risky and uncertain. Many failed. Many ships never returned. But eventually, trade routes were established, knowledge grew, and the risks became manageable. The same may happen with space. Today, launches are still costly, missions still rare, and failures still dramatic. But over time, the hope is that the risks and costs will diminish, just as they did with ships. The sea became a highway instead of a barrier. Some imagine space will follow the same path, from rare voyages to regular travel. At the same time, the metaphor has limits. The sea, for all its mystery, is part of Earth. It is bounded, knowable in scale, connected to our survival directly. Space is not bounded in the same way. Its scale is infinite, its horizons receding forever. The metaphor helps us imagine, but it can also mislead, making us think of space as simply another ocean to cross. It is not. It is more demanding, more distant, and less forgiving. Yet the fact that we use the metaphor so often shows how deeply our history with the sea shapes our imagination. What's interesting is that the parallel works in both directions. Space is described as an ocean, but the ocean is also described as space. Aquanauts are often called inner space explorers. Submersibles are compared to spacecraft. The abyss is called Earth's final frontier, echoing the language of science fiction. This mutual borrowing of language shows that humans see both realms as siblings, connected in the imagination even if separated in reality. When we think of one, we cannot help but think of the other. The metaphor also influences policy and ambition. Leaders who justify space programs often compare them to Columbus or Magellan, invoking the romance of ocean voyages. Advocates for ocean exploration use the same tactic, calling the sea our nearest space, urging that it deserves the same energy. The parallel becomes an argument, a way of framing priorities. It is not always successful, but it shows how linked the two frontiers remain in human thought. Ultimately, the parallels remind us that exploration is not unique to one environment. It is a pattern of human behavior, repeating wherever mystery exists. Whether across oceans or across the void, the essentials are the same. Courage, technology, cooperation, and the willingness to risk for knowledge. The sea taught us these lessons. Space extends them. And in comparing them, we see not only how far we've come, but also how far we might still go. As the story continues, this reflection leads naturally to another shared element: danger. Both sea and space inspire awe, but both also inspire fear. Ships have sunk in storms, submersibles have been lost to pressure, rockets have exploded, shuttles have disintegrated, and missions have ended in tragedy. Danger defines both frontiers as much as wonder does, and to understand why we go to one more than the other, we must also consider how we confront the dangers, how we accept or reject risk, and how those risks shape our choices. When people close their eyes and imagine the future, they rarely picture themselves descending into the deep sea. They picture rockets rising, cities on Mars, journeys among the stars. The collective dream is tilted upward, toward the sky, even though the mysteries of the sea are closer, richer, and no less extraordinary. This preference is not an accident. It reflects something in human psychology, the way we respond to wonder, the way we translate mystery into aspiration. The stars inspire dreams, the depths often inspire fear. That difference explains as much about our choices as budgets, politics, or technology ever could. Wonder is at the heart of it. Wonder is the mix of awe and curiosity that makes people stop, look, and imagine. When we look at the night sky, wonder comes easily. The view is vast, silent, filled with countless stars. Each point is a reminder of scale, of infinity, of possibilities beyond comprehension. To look up is to feel both small and connected. It is a shared experience across cultures and time. Every generation has looked at the same sky, told stories about it, and asked what lies beyond. That history makes space a natural vessel for dreams. The sea does not evoke the same response, at least not in the same way. Standing at the shore, the ocean stretches outward. but not infinitely. It has a horizon. It has movement, noise, and surface. It feels close, not distant. For many it feels threatening. Its depths are hidden, its waves unpredictable, its storms destructive. Wonder exists, but it is mixed with caution. The myths told about the sea often focus on monsters, dangers, and tragedies. The sky gives us constellations and gods. The sea gives us leviathans and shipwrecks. Both inspire imagination, but one leans toward aspiration while the other leans toward dread. This difference in perception influences how we talk to children, how we educate, how we inspire. Posters of rockets adorn classrooms, not posters of submersibles. Science fiction films almost always look upward, toward the cosmos, rarely downward, toward the abyss. The cultural imagery of the future is filled with starships, space stations, alien civilizations. There are few visions of a future where humanity lives among deep-sea habitats, exploring trenches, building cities on the seabed. The absence of such stories matters. It means fewer children grow up dreaming of being aquanauts, while many grow up dreaming of being astronauts. The dream pipeline begins early, and once it tilts in one direction, resources follow. Part of the psychology of wonder lies in scale. Space is limitless. It stretches beyond vision, beyond even imagination. The ocean is vast, yes, but finite. You can measure it in kilometers. You can imagine its boundaries, even if you can't see them. The human mind seems to respond more strongly to the infinite than to the finite. Infinity invites projection. It invites dreams of expansion, of eternal horizons. The sea, bounded through immense, feels less like infinity and more like obstacle. That subtle difference matters. Another factor is visibility. The night sky is visible to everyone, every night, almost everywhere on Earth. You do not need training, equipment, or risk to experience its beauty. You simply look up. That accessibility turns space into a shared experience, part of human culture at the deepest level. The sea, by contrast, hides its wonders. Its beauty exists mostly below the surface, invisible without diving, equipment, or exploration. Most people will never see a bioluminescent creature, a hydrothermal vent, or a trench. Their knowledge of these things comes second-hand, through documentaries or books. Space inspires first-hand wonder. The sea inspires second-hand wonder. And that makes a difference in emotional weight. The psychology of fear is woven into this as well. Humans evolved on land, surrounded by air. Breathing water is impossible. Sinking feels dangerous. Drowning is a primal terror. For many, the sea is a place of unease even before they consider its depths. Space does not trigger the same instinctive fear. It is unknown, but it is not tied to immediate experiences of suffocation or drowning. That allows people to romanticize it more easily. Fear does not dominate the imagination in the same way. Stories amplify these tendencies. The great voyages of history are remembered as triumphs. Columbus, Magellan, Zheng He, crossing oceans to discover lands. The tragedies at sea, though numerous, often fade in collective memory. The Titanic is an exception, but even it is remembered through the lens of disaster, not wonder. Space stories, by contrast, are dominated by triumph. The moon landing, the first steps, the photographs of Earth from orbit. These moments became shared symbols of possibility. Even tragedies in space are often reframed as noble sacrifices for progress. The Challenger disaster, for example, did not diminish the dream of space exploration. It reinforced the idea that the dream was worth the risk. The psychology of wonder forgives failure in space more readily than it does in the sea. There is also the association with progress. Space has always been tied to technology, science, and the future. Rockets, satellites, and telescopes are seen as advancements, signs that humanity is moving forward. The sea, in contrast, is tied to the past. Ships, fishing, trade, and naval warfare define much of its cultural meaning. Exploration of the sea feels historical, even if the depths remain unmapped. Exploration of space feels futuristic, even though we've only scratched its surface. That association influences where societies place their dreams. We dream forward, not backward, and the sea, despite its mysteries, feels like looking back. At the same time, the psychology of wonder has a paradox. While we dream of stars, the discoveries in the deep sea are often more immediately astonishing. Creatures glowing in darkness, ecosystems thriving without sunlight, landscapes of towering vents and canyons, all of these rival anything imagined in science fiction. Yet because they are hidden, because they are not part of daily human experience, they fail to ignite the same collective imagination. They remain curiosities instead of aspirations. Wonder exists, but it does not translate into dreams of the future. If we look closely, however, we see signs that the tide could shift. Documentaries like those by Jacques Cousteau, James Cameron, or David Attenborough have brought glimpses of the deep into public consciousness. For brief moments, bioluminescent creatures or giant squid have captured the imagination of millions. If such images became as common as images of rockets, perhaps the psychology of wonder could be rebalanced, but it would take effort, repetition, and storytelling on the scale of space exploration. Without that, the stars will continue to dominate our dreams. Ultimately, the psychology of wonder explains why humanity has chosen to go further into space than into the sea. It is not only about budgets or physics, it is about where we place our hopes. Space looks infinite, bright and promising. The sea looks finite, dark and threatening. Both are equally mysterious. Both are equally important. But our psychology favours one story over the other. As we move forward in this exploration of comparisons, it's important to remember that wonder is not fixed. It can change. Cultural shifts, new discoveries, and new needs can reshape what people dream about. If climate change, food security, or resources push humanity to look more deeply into the sea, perhaps wonder will follow. If we find new ways to tell the story of the abyss, to show it as a frontier as inspiring as the stars, perhaps children will dream of aquanauts as much as astronauts. Wonder is not destiny. It is perspective, and perspective can evolve. That leads naturally into another theme, our destiny. The debate between going upward or downward, between space and sea, is not just about wonder or resources. It's about what we imagine for our species. Do we see ourselves as destined to leave Earth, to spread across the stars? Or do we see ourselves as destined to stay, to understand and protect the planet that sustains us? This question of destiny shapes exploration just as powerfully as technology or psychology. And to answer why one direction dominates, we must look at how humanity imagines its future. When we talk about what humanity might find in space, the list is familiar. New planets, alien life, resources, perhaps even answers to questions about the universe itself. These possibilities have been repeated so often that they've become part of our culture. But what we might discover if we truly committed to the sea is less well known, and yet the potential is just as vast, maybe even more immediate. The ocean is not empty. It is filled with life, chemistry, and landscapes that remain largely invisible. If we chose to invest in it with the same intensity we have invested in space, what would we uncover? The first and most obvious answer is new species. Every time scientists send submersibles into unexplored waters, they find creatures never seen before. These aren't rare events, they are routine. In fact, it's difficult to dive into the deep ocean without encountering life that is new to science. The scale of unknown biodiversity is staggering. By some estimates, millions of species remain undescribed, many of them living in deep or inaccessible waters. Some are tiny, planktonic organisms that play critical roles in ecosystems. Others are larger, stranger, and more dramatic. jellyfish with structures unlike anything on land, fish with adaptations to pressure and darkness, crustaceans with colours that shift in the deep. Choosing the sea would mean systematically cataloguing this life, revealing Earth's true diversity in a way we have never attempted. Beyond new species lies new biology. Many deep-sea organisms have unique adaptations that could inspire breakthroughs in medicine, engineering, and technology. Proteins that resist high pressure, enzymes that function in near-freezing conditions, bioluminescent systems that produce light without heat. All of these have potential applications. Already, compounds from marine organisms are being studied for use in antibiotics, cancer treatments, and materials science. If we expanded exploration, we might find countless more. The deep sea could become a library of biological solutions to challenges we haven't yet imagined. The landscapes themselves hold discoveries too. The seafloor is not a flat plain. It is a terrain of mountains, canyons, ridges and trenches, as dramatic as anything on land. Hydrothermal vents spew minerals, building chimneys that rise like alien towers. Cold seeps leak methane, creating ecosystems fueled not by sunlight but by chemistry. Submarine volcanoes erupt in silence, shaping new land in darkness. Earthquakes ripple through fault lines, reshaping geography far below the surface. If we chose the sea, we would map and understand these landscapes in detail, learning not just about biology but about geology and the processes that drive the planet itself. Another area of discovery is climate. The ocean regulates Earth's climate in ways we only partly understand. It absorbs heat, circulates currents, and stores carbon. Yet much of this system remains mysterious, especially in the deep. If we studied it fully, we could predict climate change more accurately, model weather patterns more effectively, and perhaps even find ways to mitigate global warming. The deep ocean may hold answers to some of the greatest challenges humanity faces. Choosing to explore it would mean not just satisfying curiosity, but protecting our future. We might also discover new resources, not just minerals, though those are abundant, but biological and chemical resources that could sustain industries. Novel compounds for medicine, new organisms for biotechnology, even new food sources could emerge from deeper study. While the ethical questions around exploitation remain, the potential is undeniable. The deep sea is one of the last great reservoirs of untapped diversity. If we invested in it, we might find solutions to problems of health, energy, and sustainability. Cultural discovery is part of the picture too. The seabed holds the wrecks of ships, planes, and ancient coastlines drowned by rising seas. Many of these remain unexplored, representing a hidden archive of human history. Just as archaeologists study ruins on land, undersea archaeology could reveal forgotten chapters of our past. Choosing the sea would mean uncovering not only natural wonders, but also human stories lost beneath the waves. The most profound discovery might be perspective. Exploring the sea deeply would remind us that Earth itself is still a frontier. We often talk as if the planet is fully known, fully mapped, fully studied. But the ocean proves otherwise. To choose the sea is to admit that we live on a planet still full of mystery, a planet that requires humility. It would change how we see ourselves, not as conquerors of Earth, but as newcomers still learning its secrets. That shift in perspective might be just as important as any scientific breakthrough. Of course, choosing the sea would also bring risks and responsibilities. Exploration would reveal ecosystems that are fragile, vulnerable to disturbance, and possibly irreparable if harmed. We would face hard choices about how to balance knowledge, preservation, and exploitation. But those choices already exist. Mining, fishing, and pollution are affecting the deep whether we study it or not. By exploring more deliberately, we might learn how to manage those impacts wisely. Ignorance is not protection. Knowledge at least offers a chance of stewardship. The contrast with space is striking. In space, we search for the possibility of life. In the sea, we are surrounded by life in forms already beyond imagination. In space, we search for resources that might someday support human expansion. In the sea, we already have resources that could support industries today. In space, we search for perspective on the universe. In the sea, we can find perspective on our own planet. The discoveries differ, but both are profound. Choosing the sea would not mean giving up the stars. It would mean completing our understanding of a home before we leave it behind. The truth is that we don't yet know what we might discover, because so much remains unseen. Every prediction about the deep sea has been conservative, and every actual discovery has exceeded expectation. From glowing creatures to entire ecosystems without sunlight, the sea has repeatedly surprised us. If we committed to it fully with the same resources, vision and persistence we've given to space, it seems almost certain we would find things that defy imagination again. The unknown in the sea is not empty, it is rich. To choose it is to choose surprise. And from there, the question naturally returns to balance. Should humanity look only outward, to the stars, or also inward, to the sea? What might it mean if we shifted even a fraction of our resources downward instead of upward? How would it change our understanding of ourselves, our planet, and our future? The next reflection is not about what discoveries are possible, but about what direction humanity should take. Is our destiny written in the stars, or does it lie beneath the waves? You've been travelling with me through an idea, a long journey where we've moved up and down, into space and into the sea, comparing two frontiers that define how humanity thinks about mystery. In one direction, the stars, in the other, the depths. We've looked at history, technology, cost, communication, maps, creatures and resources. But after all of it, we're back here now. You, listening, wherever you are, perhaps sitting, perhaps lying down, maybe with the glow of a screen or the sound of something familiar in the room around you. The story, however wide it reached, was always meant to circle back to you. Because exploration, at its core, isn't about rockets or submersibles. It's about people imagining something bigger than themselves, and you are part of that story. As you've heard, the differences between space and sea are technical, political, and psychological. Yet what ties them together is the same impulse that brought you here to listen: curiosity. That impulse is not small. It's the quiet energy that built everything from the first dugout canoes to the first Saturn V rocket. It's the reason children point at the sky and ask questions, and it's the reason divers slip below the surface to see what lives there. Curiosity is universal. It may lean upward more than downward at the moment, but it exists in both directions. And when you think about it, that's what this whole comparison has been about. Not just where we go, but why we want to go at all. Maybe, as you've been listening, you've thought about your own sense of wonder. Have you ever stood under a night sky and felt the quiet weight of the stars above? Have you ever stood by the ocean and felt its immensity press outward to the horizon? Both moments are the same emotion expressed in different ways. They are encounters with mystery. They remind you that you are small, but also that you are part of something large. That feeling is not trivial. It's the root of exploration. It's the root of art, science, and storytelling. Without it, humanity would never have built a ship, never launched a satellite, never mapped a trench. Think about how much you already know about the stars compared to how little you know about the ocean. That imbalance isn't just about governments and budgets, it's about where we've placed our collective imagination. The future you've been told to imagine, the one filled with colonies on Mars, giant space telescopes and asteroid mining, is one possible future. But there's another future you've rarely been shown, one where humans live in undersea habitats, map the entire seabed, and treat the ocean as a frontier as rich as the cosmos. Both are within reach, both are choices, and the act of imagining them starts with listeners like you. You may not think of yourself as part of this decision. You may think of space programs and ocean research as things governments or billionaires decide. But public imagination shapes funding, policy and culture. The images that children see on posters become the professions they aspire to. The ideas that spread through conversations become the priorities of voters and leaders. The dreams you hold quietly, the interests you nurture, contribute to the larger currents of society. If you're listening now, you're already part of that current. Your attention is not neutral. It tilts the world one way or another. That's why this conversation about the sea and the stars is more than trivia. It's about perspective. Before humanity leaves Earth entirely, it has an opportunity to understand its home fully. Before it maps other planets, it can map its own. Before it imagines alien life light years away, it can understand the alien life a few kilometers below. You've heard how different these frontiers are in cost, communication, danger, and psychology. But the question left hanging is simple. What do you want humanity to be? A species that runs from its cradle before it knows it, or a species that explores inward and outward with equal care? As you're listening, perhaps late at night, perhaps early in the morning, take a moment to think about your own relationship to these frontiers. When was the last time you looked up at the stars? When was the last time you thought about the world beneath the waves? Which feels more mysterious to you? Which feels more inviting? There is no wrong answer. The point is to notice where your wonder goes, because that's where your imagination will follow. The truth is that both directions, upward and downward, offer limitless discovery. Space will always be there, a vast horizon stretching beyond galaxies. The sea will always be here, a hidden world beneath your feet. We don't have to choose one forever. We can choose both. But to do that, we have to recognize the imbalance, and we have to decide to correct it. That decision starts not with policy papers, but with perspective shifts in people like you. If you found this journey soothing, informative, or simply interesting, it's because the act of slowing down to think about big things changes how you feel. It pulls you out of the narrow focus of daily tasks and into a larger frame. That's the same shift explorers experience. It's the same shift astronauts describe when they look back at Earth, or divers describe when they look up from a trench at the faint glow of the surface far above. It's perspective, and it's powerful. And as this narration draws toward its pause, not an ending because the story of exploration never ends, it's worth reflecting on how easily you can connect to both frontiers even without leaving home. You can look up at the sky tonight and see the stars. You can stand by a lake, a river, or an ocean and imagine the depths. You can read, watch, listen, and learn. And in doing so, you become part of a tradition that stretches from the first humans who looked beyond their horizon to the ones who will step onto new worlds or descend into new trenches. Exploration is not only about distance, it's about attention. By giving your attention to something, you make it real in your own life. By imagining possibilities, you keep them alive in the culture. So as you go about your day, remember that the sea and the stars are not separate dreams. They are one story. They are two faces of the same desire to know, to reach, to understand. And that desire belongs to you as much as it belongs to anyone who's ever built a rocket or a submersible. Thank you for spending this time listening. In a world filled with noise and distraction, taking a long moment to think about mysteries above and below is a quiet act of exploration in itself. And who knows? Maybe one day, because people like you thought about it differently, children will grow up dreaming not just of space stations, but of undersea stations, not just of alien life in the sky, but of alien life here on Earth. Maybe one day those dreams will reshape what we choose to explore. Wherever you are, at home, travelling, maybe near a window, maybe near water, take a breath. Think of the sky above you. Think of the depths below you. Both are frontiers waiting for someone's curiosity. And in some small way, by listening, you've already stepped into them.